Hello and good morning, everyone. Welcome to 15th International Conference on Body Area Networks, BODYNETS 2020. As you can see, the conference was supposed to be held in Tallinn, Estonia. However, due to the pandemic situation, very early on, we decided to proceed conference in a virtual environment, and conference will be held virtually. My name is Mohammed Mehtabalem, and I am the General Chair this year for BODYNETS Conference. We have a very strong organizing team for conducting and organizing the overall BODYNETS Conference, including from myself. We have General Chair Giancarlo Fortino, who has a very historical cooperation and support for BODYNETS Conference. Then we had 4 program chairs, Matti Hämäläinen, Lorenzo Mucci from University of Florence. Then we had Imran Khan Niazi and Ali Imran from Center for Chiropractic Research, New Zealand, and also from University of Oklahoma, respectively. We had Publicity and Social Media chair by Frederick Rang, local chair by Professor Mart Min, and also we had publication chair by my colleague Yannick Lumulek, who have supported quite strongly for organizing this year's conference as well. BODYNETS 2020 theme is on smart IoT and big data for intelligent health management. We have quite full program for the whole day, which includes from the beginning 2 keynote speech, one from Professor Mohsen Guizani, who is an IEEE fellow, and then from Dr. Helena Gapeyeva, who is a medical doctor and specialist at of Rehabilitation Center in East Tallinn Central Hospital. We have 15 technical talks, which are covering broad range of topics on body area networks and personalized healthcare. The conference brings in 20 scientists from 10 different countries and 3 different continents. So on the left, you can see the overall program. There are 3 technical sessions for the day. We have 5 papers to be presented in each session. We may have a slight deviation from the time, just few minutes, depending upon the exact recording. As you know, it's on the virtual, so we might have some deviations from the exact time. But overall, we are supposed to follow this timeline that is presented. So thank you very much for everyone, and I hope that we will have a very conducive day and full of learning for the day from BODYNETS 2020. Thank you very much.
ladies and gentlemen, let me welcome you to the EAI BODYNETS 2020, the 15th EAI International Conference on Body Area Networks, Smart IoT and Big Data for Intelligent Health Management. I'm Kristina Petrovichova, the Conference Manager of BODYNETS 2020. Unfortunately, due to the COVID-19 emergency, I'm not able to meet you all in person. Therefore, I'm using this opportunity to address the organizing committee, the keynote speakers, the authors, and participants on behalf of the European Alliance for Innovation. Thank you for being part of this conference. In particular, I would like to thank the General Chair, Professor Mehmet Mahdab Alam, and the Program Chairs, Matti Hamalainen and Lorenzo Macci, together with the whole organizing committee, for their hard and excellent work throughout the whole process of conference preparation. I would also like to express our gratitude to Tallinn University of Technology for their support. During today's event, there are truly many ways how you can actively participate and enjoy the online interaction. During the streaming, there is a Slack platform available for all participants where you can discuss the presentations and participate in Q&A sessions. Upon receiving the link below for BODYNETS 2020 workspace, you can enter all channels which are divided into sessions. Moreover, you can vote on individual presentations and leave your fellow presenters' feedback via EAI Compass. In a moment, we will show you how to access these platforms and make the most of this unique online experience. I would also like to use this opportunity to invite you to join us for the next edition of BODYNETS in 2021. We will keep you updated and the news about the event will be available on the conference website. Should you be interested in becoming a part of the next year edition organizing committee or the technical program committee, please do not hesitate to contact me at my email address available below. In addition, if you are interested in organizing an event with EAI, such as a conference, a workshop, or a seminar, please do not hesitate to contact me at my email address as well. I will be happy to provide you with more information. Now, our community manager Michal will talk more about what EAI does, who we are, and how you can get involved in our various activities. I hope you will enjoy the conference. Thank you for your attention.
Hi everyone, my name is Michal Dudic. I'm the community manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Everyone. First of all, I would like to welcome you to our keynote session for BODYNETS 2022-20. I would like to welcome you here, and it is nice to meet you all. Specifically, I would like to welcome Professor Mohsen Guizani. It is a pleasure to have you for BODYNETS Conference, and we are happy to have you as a keynote speaker. Thank you very much for deciding to join us for the conference and for this keynote session. Hope you will enjoy.
All right, thank you very much, Christina, for this few words from your side. And I would like to briefly introduce myself. I am Mohammed Mehtab Alam, working at Tallinn University of Technology, and hosting BODYNETS Conference 2020. It's our pleasure to introduce our keynote speaker, Professor Mohsen Guizani, And I'll make a short introduction about Professor Mohsen. Professor Mohsen received the BSc with distinctions and MSc degree in electrical engineering and PhD degree in computer engineering from Syracuse University from USA in 1984, 1986, and 1990 respectively. He's currently a professor at Computer Science and Engineering Department at Qatar University. Previously, he served in different academic and administrative positions at the University of Idaho, Western Michigan University, University of West Florida, University of Missouri, Kansas City, University of Colorado, and so on. His research interests includes wireless communication and mobile computing, computer networks, mobile cloud computing, security, and smart grid. He's currently the editor-in-chief of IEEE Network Magazine, serves on editorial boards of several international technical journals, and founder and editor-in-chief of Wireless Communication and Mobile Computing Journal from Ville. He is author of 9 books and more than 600 publications in referred journals and conferences. He guest editor a number of special issues in IEEE journals and magazines. He also served as a member chair and general chair of a number of international conferences. Throughout his career, he received 3 teaching awards and 4 research awards. He's an outstanding researcher in wireless communication and ad hoc sensor networks. He was chair of IEEE Communication Society of Wireless Technical Committees and chair of the technical committees, additional technical committees on IEEE. He served as a IEEE Computer Society Distinguished Speaker, and he's currently the IEEE ComSoc Distinguished Lecturer, and he's a fellow of IEEE and senior member of ACM. So it's been really a pleasure to have you, Professor Mohsen, for our keynote talk on BODYNETS Conference. And the floor is yours. Please tell us about IoT security schemes for healthcare systems. Thank you.
Thank you for the nice introduction, Mohammed, and thank you for the invitation to serve as one of the keynote speakers for BODYNETS. Again, when we first talked about this, remember about 2 years ago, we planned a trip to your institution and a good visit, but next time. Today, I would like to talk about some security schemes, lightweight security schemes that we are developing for IoT devices that we are using in healthcare. And let me start by the introduction. This is the outline for the talk today. After the introduction, we'll talk about some research activities that we are developing here. And then I will select some projects or topics to talk about the implantable IoT devices and their security schemes, and then some research plans for future directions. So towards a smarter future, as you know, the systems around us are getting smarter every day, and therefore we would like, as technical people, we would like to develop some apps and some applications that will serve the human being to improve the use of energy, the use of mobility, or developing smart mobility in vehicular communication. The use of water. As you know, water is very scarce and very important all around the world. So there are schemes now to conserve water, especially in the agriculture technology. Public services, improving public services, smart devices, using IoT for smart buildings, and the smart data centers. So I won't read all of the details under each, but the common theme of all of these applications or of all of these things around us is how, or the common challenge is how to integrate all of these to work well, to be smart, to conserve all of these, and to be environmentally friendly. So we expect that the ubiquitous IoT devices that are available around us will serve this goal, and will be able to provide us with better services to achieve the smarter future and provide smarter services to individuals. So what would, if that's the case, then what would be the technology that will support all of these? As you know, that cloud to serve as the control and to serve as the storage for all our data, because as you expect, these IoT devices, they will collect from all of these applications that I described in the previous slide. They will collect a tremendous amount of data, and that data has to be delivered somewhere, has to be stored, has to be then analyzed, and experts then will make the appropriate decision for whatever application that we mentioned earlier. So the cloud turned out to be, with the huge data that we are collecting with these devices, the cloud turned out to be loaded, and the delay is tremendous. So therefore, we resorted to what's called the edge. That means we said, okay, well, why don't we get closer to the user, get closer to the data collection, and try to push some of these functionalities toward the network edge, so that they'll be closer and the delay will be less. And then we will try to distribute, rather than having a control place or a main server, we will try to distribute the functionalities and therefore reduce the load. And then people now are even talking about what's called mist. Mist is something that is much closer than the edge, not at the network edge, but it's for instance, if we're talking about a group of people in meeting in a room, if Muhammad has downloaded already a video that I want to watch, rather than go to the edge or to the cloud to download the same video, I can get some portions of some pixels of that video from Muhammad. I can get the rest from Christina and the others from Mati, because we are in the same room, and that would be closer to me, and I would be able to use it. So we are talking now of billions and billions, as you know, of IoT devices that are distributed around us, and that they will be collecting this data. And the challenge now is to be able to store that data, in particular, to analyze that data and make use of the information that is collected, because the data is huge and is tremendous. So toward that goal, our research activities are around three themes, as you can see in the slide: large-scale IoT deployment, fog and cloud computing, and then the different applications that we will use these into. And both when I were in the US and here in Qatar, these are some of the agencies that support give us some money, some grants. As a matter of fact, the talk that I'm going to present today, the results are based on a NPRP grant, $1 million that we got from the Qatar National Research Fund for developing some lightweight security for these IoT devices. So as you can see, I won't read all of these, but the applications of these from healthcare to cybersecurity to smart city to vehicular, and going to future applications which include complex systems, whether be it the smart grid or the financial systems or the automotive systems that are around us. So in order to achieve this smarter future, we have to enable a smart and secure living. That means we're talking about intelligent mobility. If we are talking about applications in healthcare, we need to look at what kind of IoT devices we will use to collect this data and analyze it efficiently. How about blockchain? Can we use blockchain for healthcare? How about intelligent transportation? Everybody these days is talking about machine learning and artificial intelligence, as you all know. How can we use those in order to achieve this smarter future that we're talking about and making a smarter living for all of us? As you can see, these descriptions or these research themes or research topics involve not only the solo researcher that we used to in the past, but it's all interdisciplinary. For instance, if we are talking about smart city, I was talking to, when I was at the University of Idaho a few years ago, I was talking to a city planner, a professor at the architectural department, where we were talking about how you guys plan a city. In our current research about lightweight security schemes, we're talking to a medical doctor. As a matter of fact, a medical doctor is listed with us, is involved in the proposal. Because the things that we develop, the schemes and the algorithms that we develop, we wanted to we take it to the hospital, and we try to implement them on the devices that these medical doctors or nurses use, so that we can see how efficient they are. So you can see the list here. I won't read it, but it involves human factors. If we are talking about vehicle, automotive driving, if we're talking about use of artificial intelligence, if we're talking about intelligent transportations, intelligent health systems, and so on and so forth. So if we go back now to the topic of this talk, is the healthcare. As you know, healthcare expenditures have been skyrocketing in the past few years, and as you can see from this figure, it shows that by the end of 2018, healthcare expenditures in the US alone. And you know, US is not providing healthcare to every individual, so I expect it to be much more in the European countries, where it was expected to exceed $4 trillion US. So that's a humongous, that's a huge. So if there is any way that we can try to reduce a little bit here and a little bit there of this cost, then we would achieve a lot. What do I mean by a little bit here, a little bit there? For instance, reduce the we have a lot of elderly around the world, especially in Europe, as you know. So if we can monitor the elderly would like to stay at their homes. If we can monitor them from their homes and have some technology that monitors them and provide real-time monitoring, then be it. They will be happy at home. Will reduce the cost of taking them to those home cares, or taking them to the hospital, care for them in the hospital, or for instance, for people who are going through surgeries. I mean, rather than keep them for a week or two after surgery in the hospital, we can reduce that amount of time and therefore reduce and use IoT devices to monitor those and provide service as need be. So the question is, or the questions for us as academicians and researchers is can we use any of these new technologies or new research ideas to reduce this cost? In particular, now we are focusing on healthcare. How about the first question is IoT? I mean, IoT is now ubiquitous, is available, is being used. I mean, it has its own advantages, pros and cons, but can we use that to achieve this goal? Can we use blockchain to be able to achieve some of these goals? How about machine learning and artificial intelligence? So today we'll concentrate only on the first question and try to shed some light on that. I mean, I'm not going to claim to give all the solutions, but the point is to come up with at the end with what are the future directions, research directions that the attendees of BODYNETS would take with them and would discuss in the research community and with their graduate students and undergraduate as well. So if you look at IoT and its use in healthcare, I mean, this is IoT being used in different industries or different businesses. We can see, if we focus on healthcare, you can see that IoT is so important in healthcare. It provides about 61% of support to healthcare. And so when we talk about IoT in healthcare, we are talking about sensors. I mean, the usual sensors that we know, for example, that are available with our smartwatches, our smartphones, what have you, our wearable our wrist watches, our wearable suits, if they are now embedded with IoT. So those devices will collect the data, whether being a patient or not, and provide that data to a platform, whether be it at the cloud, at the edge, or at the mist, as we mentioned earlier, and analyze that data and provide then provide that analytics to the experts, to the personnel, to health personnel in this case, to provide based on that information, to translate that to health data into actionable insights and actionable actions for us, for whether being patients or non-patients. In particular, if we are talking about we found out that the major challenge is, how about these miniature devices, these very small devices that we call them, in the medical field, they call them implantable medical devices, IMDs. These implantable medical devices, as you know, they can be brain stimulator, they can be heart defibrillator, they can be artificial knees, and so on and so forth. So these are manufactured to replace a missing biological structure, support a damaged structure, or enhance some of our body services or functionalities. So in our case, so these IMD devices or sensors, let's say, these are so small. Think of the pill that a patient swallows that has a camera that will send information or send video pixels to the central or to the computer system, so that we can analyze the pictures coming from the intestine or the stomach of a patient who has a problem with digestive system. So and these are not used, the IMD sensors are used in neurological systems, they're used in cardiovascular, orthopedic, and even cosmetic these days. So the challenge is that these implantable medical devices, they are so small, and therefore they don't have enough computing power or enough energy or battery power that they can process things normally, okay, that we can process in other sensors. They cannot use cryptographic algorithms that we use in our laptops or in our computers today. They cannot use the regular batteries that we use in our smartphones or in our computers or laptops because we have to have a surgery to be able to replace the battery. So we cannot provide surgeries every year or every week or every 2 years, for that matter, in order to replace a battery of a cardio defibrillator, for instance. So we have to therefore develop lightweight encryption schemes so that we can use them in these devices. Avoid invasive operations, and provide efficient ways for short-range communication. So we need to develop these schemes to give access to only authorized entities. Make sure that the medical logs are always accurate, so that, and secure, of course, so that authorized people can access anytime, and to be able to, a medical doctor can click a button on his or her platform in the medical system, so that they can get the information quickly and accurately. They should be always available to authorized entities, and they should reconfigure most of. So if a regular security system is realized by the functionalities you see on the left side of this figure, then if it's for health, it has to be more reliable, more efficient, more quality, because we are talking about our health and its health of all of us. So coming from the communication perspective, when we got this project, we said, okay, let's look at these implementable devices and see how we can help developing these lightweight schemes. So we found out that starting from the beginning, we found out that there are two types of attacks. There are the internal attacks, as you can see in blue on top, in this figure, which are these internal attacks are built in or within the hardware itself. So we were not interested in these types of attacks. We are interested in the external ones that come from the communication. That is eavesdropping, man in the middle, denial of service, and so on and so forth. That can be created from the communication part. So we took the insulin pump for diabetic patients as an example. The insulin pump, and we have developed that 3 models that I will briefly talk about today. The first model is what's called using Diffie-Hellman. Diffie-Hellman is using only one parameter in the system, and to explain that briefly. Of course, we have publications on this, and the details are in the publication, or I can give in the questions later. But assume that we have an insulin pump here for a diabetic patient, and we have a remote. Of course, the insulin pump is surrounded by different sensors and devices. But if we look at the remote gadget that is supposed in the hand of the patient, and he or she has the insulin pump and would like to increase or decrease the insulin level, be it required, whether it changes during the day or it changes during the week. Depends on the type of diabetes and the type of a patient. So that short communication from the remote control to the device itself, the insulin pump device, is a signal. And we looked at the signal and we said, okay, so the signal, what if we send the same signal again and again, then an eavesdropper will be able to get the format of the signal, as you can see down here, and will be able to recognize or recover some of the information that and eavesdrop on this. So we said, okay, we looked at the format and we realized that the device pin, and we asked the experts, and we realized that the device pin is not, I mean, it's a number that is not a number of bits, that is not necessarily for each. So we thought if we can change this device pin by a Diffie-Hellman code, so that code, that simple Diffie-Hellman code will change every time the patient or the remote control will communicate or will send the signal to the insulin pump, then we can the eavesdropper or the attacker will not be able to recognize the format of the signal every time there is that communication, and therefore the attacker will be confused and will not. So you can see, one can say this is too simple. And that's the point. We want it to be simple enough. Because we don't want any processing, any computing done, or any processing done, or any energy to be spent on this. So to our surprise, when we looked at the NIST table to compare this of what we can achieve by doing this simple change in the signal format, you can see the ones with the X's here. We could defend against them, spoof attacks, man in the middle, replay, and so on and so forth. So it really was very successful in trying to achieve a lot of by confusing the attacker. Can we refute that 100%? No, because we are using only one parameter. As I said, in the Diffie-Hellman, we are using only the device pin. So we said, okay, how about if we can use more than one parameter? That brought us to model 2, where we use what's called the chaotic Henon system. Henon, or Henon chaotic system. Henon is a mathematician, a French mathematician, who developed a mathematical system that is based on two parameters. These two parameters are called the seed and the initial conditions. The seed, I mean, I present here the equations of the Henon's chaotic system. Okay, so the chaotic system, as I said, is based on the hypersensitive initial conditions and a seed. Usually the seed is something like the frame check sequence, where or the generator polynomial, where both the sender and the receiver will agree on what generator polynomial will use to compute the FCS or the CRC. So the seed, even if the seed is being compromised or being eavesdropped or being hijacked, then we have the other parameter, which is the hypersensitive initial conditions that can change every time, and will not be able, the attacker will not be able to achieve that. And without going through the mathematical details, we also analyzed this, and we used the NIST table, and we can see here in this table we passed all the tests. So we have improved even though it's still very simple, we are not consuming any computing power or anything. So the goal or the idea is to change the pattern every time we send or communicate. As you can see here, I show some patterns every time pattern configuration every time that remote control device is communicating to the diabetic device. So you can see here the patterns change every time, and therefore there are no recognizable patterns to give hints to the attackers. So this is the model 2. Model 3, which of course I think you know model 3, and some of you may have used it, is biometric. Means how can we use our fingerprints, our iris, our heartbeat, for that matter. It changes from one to one. So this is we want the system to learn from the body, because these devices are implanted in our bodies, and therefore they can be charged by the body heat or the heartbeat, and then can also learn or can be trained, like using machine learning or artificial intelligence, can be trained to learn about the system and to update based on the need. So here's a photo in the lab of what we are doing, and we are still working on this model 3. So the idea is that how we can develop a lightweight, efficient, and accurate, and adjust and recover, a scheme that adjusts and recover based on the need of the patients, based on the need of the healthcare provider. So a few years ago, I received a master student whose bachelor was from biology. And he wanted to do his master with me, and we were talking about what is done in biology and how we can adapt some of the biological systems in such a situation. So we were talking about the immune system, and I said, look, John, if we can think and develop. Can we think and develop a lightweight algorithm or a security scheme that will think like our immune system? That means a system that can learn and can automatically diagnose or recognize the virus, be able to develop defense systems against that particular virus, because the viruses, as you know, differ from one person to the other, from one time to the other, and so we came up with this scheme, a lightweight, efficient, and accurate adjust, and we published initial results in a conference, but we're continuing this using immune systems. So we believe that the future for developing security schemes or privacy measures for in a network system should follow the human immune systems, or should use be realized like the human immune system that we think about. So these are some of the ideas quickly of how to think smartly, to be able to use these IoT devices, to be able to develop lightweight schemes, whether be it for security or for others, for other applications. So to extend this work, I mean, we have developed some of these schemes, but we also there is a lot of opportunity to extend it to other body features, as you know, that we use it only for the level of diabetes and diabetics, and only to the communication between the remote control and the system. How about power consumption optimization? I mean, we have to optimize the power consumptions, as I said, so that we don't have to have a surgery for these people to change the battery or to give energy to these devices. Enhance the learning algorithms for using other algorithms. We used Diffie-Hellman and Henon, but we did not use genetic algorithms, for instance. We did not use water filling and other algorithms for that matter. So we can extend this. When we say IoT, we are not only, we look today at only the communication part. You can see from the top of the slide, the IoT is a combination of identification, devices, sensing, communication, computing, computation, services, semantics, and so on and so forth, that is used in many different applications, as you can see on the bottom of this, whether be it remote health tracking and monitoring, as I mentioned earlier, whether be it intelligent transportation and traffic management, whether be it troubleshooting and diagnosing and repairing some of the equipment that is used in whether in very complex systems like the grid, for instance, the power grid, or in very prohibitive places where we have chemical spill or places that we cannot access. So these requirements and challenges that we are looking at are or possible extensions are resource dimensioning and allocation. For instance, service availability and connectivity. So as you can see here, we concentrated only on how to develop very minute problem we are talking about here, or objective we are looking at is the developing lightweight schemes for IMDs. How about service availability and connectivity? How about the workload of these? How about predicting future uses and applications? The second is the service level agreements and the quality of service. I mean, these different patients or different monitoring systems, they have different quality of service or quality of experience requirements. Do we use cross-layer awareness? What about the admission control and selection? How about if we don't have the proper hardware and equipment and the space to do the experimentation? How about system virtualization and embedding? What about the virtualization algorithms, the slicing that we use, network slicing that we use these days? How about reliability and predictability? Enter cloud and interoperability. For instance, if the system, if what I developed and talked about today, these models, if I develop it to work in a system like in a country like Qatar or in any country in Europe, would that work if it's is it scalable? Would that work if I move to another city or move to another country for that matter? Because there are different legal issues, different policies, different guidelines. So that goes back to the interdisciplinary work that we have to talk to medical personnel, we have to talk to legal people, and also what about most of these development of these experiments are using devices off the shelf? What about the robustness of the network? If we are using a simple experiment, but now we want to deploy it into a big network or a big system like in Europe or European Union or in the US. Or in China, it would really be very different now because you are deploying it now for use. It's no longer the prototypes that we do in the lab. So that's the first one. How about the safety and security of patients in terms of saving their data and only give authorities to personnel that are allowed to access. But also, when we are working on this, I discussed with my students on how now we develop these schemes. They seem lightweight. They work most of the time. But we are saying we give access only to authorized personnel. What about if there is an emergency? We're talking about health systems. How about if there is an emergency and somebody fell down in the street? and because of low sugar or high sugar. How about how can bystanders can help? It's an emergency system. So we developed another system where we can give access in an emergency when your wristwatch or smartphone realizes that there is an emergency, or you are dizzy, or you fell down, then it may give special access to certain people. So that's how about ethical issues when we have to, as I mentioned in the previous slide, legal issues and different quality of experience, different quality of service. And how about if you move somewhere else, if you move to another city or another country, what about the policies and regulations? So that's in a brief about some discussions about these. And thank you for your attention. And I open now the floor for any questions you have.
Hello, good morning, everyone. Welcome to the second keynote speech of the BODYNETS Conference 2020. It's our pleasure to have with us Dr. Helena Gapeyeva, who is a medical doctor expert and working at the East Tallinn Central Hospital in the Department of Clinic of Medical Rehabilitation. She has quite a vast background and experience in the healthcare. Graduated from University of Tartu from Estonia, and have been working at different places in Estonia for ministries and on a number of different projects and European projects. So it's really our pleasure to host Dr. Helena today. And she is going to tell us about her research on movement analysis in physical and rehabilitation medicine, data monitoring. So Helena, thank you so much. And please, floor is yours. You can start the presentation.
Thank you for introducing.
And
my presentation devoted to movement analysis in physical and rehabilitation medicine regard to data monitoring. Tense is my research topics and collaboration, multidisciplinary team in physical and rehabilitation medicine and areas of medical rehabilitation, human movement estimation, sensors and movement analysis systems, instrumented gaits and movement analysis, dual and multiple task training systems in VRM and future studies. My research topics and collaboration shortly. I graduated University of Tartu, Faculty of Medicine, Department of Sports Medicine, and received FD degree in Faculty of Exercise and Sports Sciences in Kinesiology, and worked as researcher in University of Tartu, Laboratory of Biomechanics, and now I am physician of physical medicine and rehabilitation in East Tallinn Central Hospital Clinic of Medical Rehabilitation. I participated in multiple grants of Ministry of Education of Estonia, Estonian Science Foundation, Estonian Ministry of Defense, and also European grants from Ministry of Foreign Affairs of Italy, European Union, Eurostars programs, and also FP7 frame RAMS program, MyOH. Main research topics are biomechanics of movement, neuromuscular performance, physical and rehabilitation medicine, and orthopedics and traumatology, pre- and post-operative rehabilitation of neuromuscular system, adaptation of neuromuscular system to physical training, work-related musculoskeletal system problems. Also, I am functioning as a member of different scientific societies, including the International Society of Physical and Rehabilitation Medicine, European Society of PRM, and European Society for Movement Analysis in Adults and Children. Let me introduce to East Tallinn Central Hospital and Clinic of Medical Rehabilitation, which was founded in 2012. And head of clinic is Heidi Alasek. So what are our outpatients and inpatient medical rehabilitation services? Also, we have teaching cooperation with University, Tallinn Technical University, University of Tartu, and also cooperation with applied schools of education and nurses, occupational therapists, physiotherapists. And main areas of rehabilitation in our clinic is neurologic, stroke, cancer of CNS, orthopedic, rheumatologic, cardiologic, post-amputation rehabilitation, sports medicine for prevention program and post-injury rehabilitation. Along the way, I worked in University of Tartu in Laboratory of Kinesiology and Biomechanics, which was founded in 1982. After my graduation of university, we worked all together with our colleagues, Mati Pasuke, professor, Jan Helena, lecturer, me and Tatiana Kums, assistant. What is a multidisciplinary team in physical rehabilitation medicine and which areas of musical rehabilitation? As you know, rehabilitation team devoted to patients and family orientated also, and physicians, physiotherapists, nurses, social worker, occupational therapist, clinical psychologist, prosthetists, speech therapist, limb therapist, masseurs, caregivers, and dietitians deal with patient's problem and decide a future rehabilitation plan. By date of our hospital for second rehabilitation department, patient distribution by pathology was next, that on first place were arthroplasty and arthritis problems, second place injuries, and last problems were connected with spondylopathy, other bone joint and muscle diseases, brain vessel diseases, and other neurological problems, blood circulation diseases, inflammatory joint disease, cardiological and oncological very low level. Which purpose of physical and rehabilitation medicine? They mostly next assessment of patient functions, objective estimation of musculoskeletal and other functions, discussions of the aim of physiotherapy and other treatment methods, plan of intervention and correction of plan if needs, and compiling of recommendations for home-based therapy. Next topic is human movement estimation, sensors and movement analysis systems. As you know, estimation of human movement is complex problems, and aims could be different depending on patient needs or client needs. And for example, it could include gait and posture, movement analysis, sport exercises, and technique study. Also, recently it was used gait capture in automatic emotion recognition. Also, movement measurements in psychiatric care of elderly patients. And for this aim, different types of sensors are applied. They could be wearable, environment embedded, implanted, and other. On this slide, you can see movement analysis system classification, which are given by Guizani et al. In previous year. Here is given gait capture systems, which mapped in a two-dimensional space from lab-based to home-based, and from wearable systems to vision-based systems. Advanced in sensing and computer vision technology allow gait monitoring and analysis to be performed at home. So, from this schema, we can see that systems for gait analysis could be wearable and vision-based, also with using of reflective markers, also markerless systems, wireless inertial measurements units, sensors or accelerometers, and also using body mass pressure distribution methods. Here you can see a C-mill device on treadmill, where is force plate embedded for gait analysis performance in lab condition. So here is possible to analyze gait cycles and impairment in patients with amputees also. Same devices is used for analyzing of gait asymmetry, and it is possible to do recommendation to for rehabilitation of and to decrease of impairment in future. Robust computer vision algorithms have been developed to extract key joints in real time and subsequently estimate gait characteristics. And for this is used markerless vision-based systems with RGB cameras and RGB-D cameras, which don't require wearing specialist equipment. Here you can see axis, which applied in Kinect type devices. But as notes, it could be demonstrated that also this system can accurately be used for gait analysis, activity recognition, and energy expenditure estimation. They pose risks to the privacy of subjects, which limit their acceptance. Here you can see a walkway with Kinects for Windows from Microsoft in Amsterdam University Medical Center. They are using a long way, approximately 20 meters, and multiple cameras, which analyze movement of subject, and it is possible to self and reproduce data of gait analysis or movement analysis in patients with different pathologies. Systems analogous to center of pressure distribution are used wide vault, and here is example of baropodometry system from diagnostic support of where you see sensors embedded in force plate, and also is possible to perform a gait analysis by measurement of changing of COP during gait, for example. Also, pressure insoles could measure ground reaction forces, and here you see example of sensor products, sensors. Electrogoniometers based on flexible sensors measure the angles in different joints, on ankles, knees, or hips. So it is possible also to perform movement analysis using these devices. Recently, more in use inertial measurement units, sensors for study of human gait, They can be attached to any part of the body. Most of them are the set of accelerometers, gyroscopes, and magnetometers to measure velocity, acceleration, and position related to gravitational forces. Here is a sample of so-named G sensor of BTS Bioengineering Company, which is possible to wear on waist and perform gait analysis inside room or walking on bigger distances. And it is possible also perform not only walk, but also jumps analysis if needs. Also, the airborne activity recognition sensor allows patients to be continuously and discretely monitor their gait and activity levels independently. But some notes for wearable devices, they require subjects to cooperate and tolerate them. But for elderly people and patients with Alzheimer's disease or dementia, it is common to forget to wear the devices or to be unable to use them. And also, this may result in further agitation for subjects with mood diseases. Last year's 3D gait characteristics have been monitored from radio signals, provided information of movement of subjects, even through walls, the so-called invisible devices. Next topics, instrumented gait and movement analysis. Marker-based multi-camera motion capture systems include multiple sensors or reflective markers on anatomical points of the body to capture the joint movements with high precision. Also, force plates record ground reaction forces, sensors placed on the floor or a treadmill to evaluate the pressure during walking. The forces exerted on the sensors are related to the load exerted to the joints. Also, during gait or movement is performed electromyography record for muscle activity measurements. What is the main aspects for these marker-based multi-camera motion capture systems? That it is possible to use this in large clinical centers or specialist laboratories. Which advantages of instrumented gait and movement analysis? With help of these systems, we can receive most objective information to identify and analyze walking, posture, or movement problems, including kinematics and kinetics data. Also, the digital synchronization of infrared cameras, force plates embedded in walkway, and video caption helps to simultaneously search and compare the patient's pattern of movement of body segments and power distribution during different phases of motion. As you know, instrumented gait and movement analysis is provided by two types of hardware, with floor embedded force plates or moving belt, uni or dual belt embedded force plates. Firstly, for performing instrumented gait analysis, we had to choose human body model for our aims. They are different, and it is possible to use full body with arms or without arm, only for trunk and lower extremities. The placement of cameras depend on space in room and also numbers of cameras what is possible to use for analysis of gait and movement. It is traditional displacement of cameras in room, cameras from 1 to 6, for example, where walkway is located in middle of the room with force plates embedded in the floor. And as I say, the optical cameras record reflective markers movement. And before this, we have a valid human body 3D model. And after, it is possible to monitor data and calculate data for future analysis. Here is example for marker set for subjects in laboratory of kinesiology and biomechanics of University of Tartu, and set of markers. The diameter of spherical reflective markers here is 1.5 centimeters. So different shape is possible to use also half spherical markers too. Program will check the placement of markers on the body and record body movement in 3D room. Different infrared cameras are using for this aim, but their speed could be enough for recording of body movement. Different marker sets and cameras used by different labs. Here is example of gate lab in clinic of Sint Maarten, Nijmegen, the Holland. And other variants, it is gate lab in Amsterdam University Medical Center, where you can see force plates embedded in the floor and camera set from different position. Here also different position of markers and rooms in lab, and which tests is possible to use in physical and rehabilitation medicine. As example, it is possible to perform gait analysis, body posture estimation, staircase walk, chair rise, and step test, for example, and also other possibilities. Here is example of 3D movement analysis systems in laboratory of kinesiology and biomechanics. You can see two force plates of Kistler embedded in walkway in the floor and reflective markers for human body recording. Here you can see example of gait analysis and sit to stand test for person with brain injury after brain injury. The cameras looking movement of markers, and we can see distribution of forces also, which influencing on different joints of human body. And also here we can follow the moving of lower extremities and also trunk during walking. And to compare different gait cycles for one and right leg and other left leg, and to compare these characteristics. Main characteristics which is possible to monitor using instrumented gait analysis are kinematic and kinetic characteristics. And also it is possible to see in graphs for kinematics and kinetics for hip, knee, ankle joint, for example, differently. Dynamography of gait and movements of posters or poster is used to monitor ground reaction forces components and also center of pressure displacement during gait of poster. You see on force plate, depend on direction of movement, we can analyze vertical, anterior, posterior, and medial lateral forces of ground reaction forces components. Also here, we can see different variants, ground reaction forces and center of pressure displacement during gait on the curve. On y-axis, we can see forces, and x-axis, gait cycle. And until 60% of gait cycle, we have a stance phase, and correspondingly ground reaction forces, vertical ground reaction force, medial lateral, and anterior posterior ground reaction force. The forces are different when people are walking barefoot or using sport shoes or using walking boots, for example. Gait cycle characteristics a little bit differ by presenting of different orders, and here is example of gait cycle distribution by Vaughan and al. In 1999. So we can see 8 main phases of gait cycle. Initial contact, loading response, response mid-stance, terminal stance, pre-swing, initial swing, mid-swing, and final swing. Gait stance phase, as I said, it includes 60% of all gait cycles. And so it is possible to analyze different gait stance phase by parameters. In rehabilitation medicine, it is very significant which mechanism gives more influence on gait impairment, and it is possible to find which factor or mechanism has most effect on this ankle mechanism, knee mechanism, or pelvic mechanism. Here you can see example of knee joint kinematics during gait, where you see different data for knee flexion extension, knee abduction and adduction, and also knee rotation parameters. And here you can see marker placement for knee joint movement estimation. Here is example of a study of knee joint extension flexion moment change in women after arthroplasty. And for example, on this curve was analyzed knee extension flexion moment for one gait cycle pre-operatively, 1 day before operation, 3 and 6 months after operation during mid-stance. And you see that if pre-operatively data were a little bit lower as compared to 6 months after operation during mid-stance of gait. And which data in regard of knee joint power at mid-stance. Also, you can see that if pre-operatively it was significant difference between operated and non-operated legs, and also as compared to controls, 6 months after operation, these characteristics did not return on pre-operative level and also did not achieve the level of controls person yet. So for rehabilitation of this group of patients, more time we need for rehabilitation goals achievement. Other systems for gait analysis, so named zero gravitation, example of this movement analysis systems in Sint Martens Clinic in Nijmegen, Amsterdam. So people can walk during this walkway, and also it is possible to eliminate body weight or decrease body weight influence on body during movement. Recently used 3 body weight support system or Ryzen also in lab situation in Amsterdam University Medical Clinic gait lab for person post-stroke or with other neurologic problems with body weight support system, 3-dimensional. It is possible to regulate gait characteristics for people who independently cannot work, and using chair for movement. Best possibilities for performance gait analysis using virtual reality is possible with gait real-time analysis interactive lab systems, where force plates embedded in dual belt moving treadmill. Same marker sets, for example, is possible to record gait analysis or movement analysis of patients. Other possibility for environment embedded for movement environment possibilities gives using of computer assist rehabilitation environment system. You see here implanted dual belt gait analysis system, dual belt embedded force plate, and also this system gives possibility to rotate so-named floor surface around this system, spherical system, and it gives best possibility for training not only motor functions, but also cognitive and other body functions related to aims of rehabilitation. Next topic, dual and multiple task training system and physical and rehabilitation medicine. As I said, with conventional therapy, patients are limited in training gait stability, and new possibilities for task-specific training are open with virtual and augmented reality. And for this aim is used Gait Real-Time Analysis Interactive Lab System, or GRAIL, which have dual belt treadmill in virtual environment. It was noted that virtual reality is a helpful tool to train gait adaptability by projecting stepping or obstacles on the walking, running surface, and to add cognitive elements for dual task performance. And significant, it is possible to give positive feedback to patients. Recently, in 6-week randomized controlled trial, where participants number was 282, virtual reality-based treadmill training decreases fall rate as compared to regular treadmill training in older adults. Here you can see possibilities of using GRAIL system, dual belts force plates for patient with leg amputee, and also it is possible to do different training or testings modalities. For children, it is possible to use also cognitive physiotherapy using virtual reality, and such example is given in Amsterdam Medical Center of University Virtual Reality Lab, where children did not afraid in using these modern technologies, and what is significant, they participate in this with optimism, and possible to study children behavior and also cognitive function impairment with using these systems. In our hospital, we also performed training with GRAIL system with different aims. For example, in present figure, you can see training of body balance. And for this, subject had used both legs and trunk muscles to keep equilibrium and to move object in different positions, anterior, posterior, medial, lateral, and also in vertical displacements. On other kinds of trainings, patient had achieved some goal. What is significant, it is possible also use, if we need body support system in case of patients who are not able to keep body posture stable during gait or movement analysis. What is significant, patients have feedback, what is a big motivator factor for a rehabilitation program success in patients. Here is one example of data of patients with knee injury performed on GRAIL system, which is significant for diagnostics and also for decision making. In this table, we can see spatiotemporal characteristics mean walking speed, for example, mean stride length. But what is more significant, we can see different for injured and non-injured leg in real time, mean stance time, swing time, stance time, persons of gait, and also mean swing time, persons of gait cycle. You see difference more than 4 persons for between legs of these patients. And also curves, we can analyze kinematics data, joint angles for right and left body sides, and also kinematics for left and right body side for different attempts. What we can conclude for future studies? Which problems could be elucidated in future? Unification of data monitoring, including standard software protocols, is the best way to exchange the information between different hospitals and research institutions. Previously, it has been supposed to build online database for monitored data, but future studies need the in-network processing and security aspects for this aim. Big problems were that across subjects, data variability is very high for some methods. And also, future clinical research could be applied in clinics for using smart sensor technologies and also using mobile applications. What is take-home message? For successful long-term rehabilitation, we need positive cooperation with patients and family members, multidisciplinary teamwork, evidence-based diagnostic methods, lab and home-based together, standardized protocols, and also longitudinal evaluation and correction of tasks. I would like to thank East Tallinn Central Hospital and Head of Clinical of Medical Rehabilitation, Dr. Heidi Alasep, and colleagues for helping medical rehabilitation topic. University of Tartu, Head of Laboratory of Kinesiology and Biomechanics, Professor Mati Pasuke, and colleagues Jan Erlina and Tatiana Kums for many years collaboration in lab. Professor Emeritus Tit Haviko for support of scientific studies. Also Head of Institute of Sports Sciences and Physiotherapy, Professor Prit Kazik for support of lab. Also, I would like to thank Associate Professor Manuela Galli from Politecnico di Milano for her enthusiastic support with knowledge of movement analysis. And also, EAI and ERDF for participation in BODYNETS 220, as is what support by organizing committee and ERDF. Thank you for your attention.
Thank you so much, Helena, for a very comprehensive talk on gait analysis and methods for rehabilitation. I think it's a very, very important point, and taking the few points from your features, it's very critical to combine the efforts and unify databases. Thank you so much for your talk and presentation. And here I would like to close this talk, and we'll take the questions from the audience.
Thank you.
Thank you.
Okay, may I have a question?
Okay, please.
It relates to this rehabilitation using virtual reality environment. So
Yes.
I think especially with the children, or of course also with adults, is there any studies carried out comparing the results if you have used virtual reality environment or not? So is it improving the healing process?
Yes, it is discussed about monitoring data for children. It is very different, and mostly movement analysis for children performed in floor embedded force plates, because for children it is very significant to move with certain velocity. As I know, on dual belt embedded system using virtual reality, the age of children began from 6 or approximately this year. And colleagues from the Netherlands University Medical Center did experiments with children gates, and they confirmed that virtual reality using improves children's ability, cognitive function. But for gate data, I recommend maybe to use initially flow embedded system, and only then to use dual belt system for gate characteristics analyzing.
Thank you.
Thank you very much, Matt, for your questions. So we'll take further questions, hopefully from the audience live. So thank you very much, everyone, for joining this session for this recording, and we'll continue from the conference. Thank you very much. Thanks very much, Helena, for your keynote talk. Thank you.
Thank you.
Hello everyone, I am happy that I have been given an opportunity to present a paper. My name is Ikrar Ahmed and I am a PhD student in Center for Wireless Communication at the University of Oulu. I am a co-author of this article. The title of our article is Providing Connectivity to Implanted Electronics Devices, Experimental Results on Optical Communications over Biological Tissues with comparison against ultra wideband. So the outline of my presentation today is, firstly I'm going to introduce the topic, then the comparison between radio acoustic and optical wireless communication has been presented. In the next section we'll show the experimental testbed we have constructed for our study, and finally we would have our results analysis, and then I'm going to conclude my presentation. So without any delay we move further. We are using wireless communication in almost like every situation where we need to transmit data or information wirelessly, and we are using mostly radio frequencies for this purpose, such as in mobile communication or Wi-Fi routers, and so on. We have been using it for the betterment of human healthcare as well, such as in self-care, where we have been tracking our chronic illnesses by using different sensors to assess different onsets and different healthcare parameters. One such example is like is monitoring the blood pressure and SpO2 sensors, etc., and so on. So the development of IoT and wireless body area network are typical examples. Another important application is wireless implants such as wireless pacemaker and defibrillator, which are capable of transmitting and receiving data wirelessly, and that uses the radio frequencies for those wireless transmission. So basically all these development surrounds around human. That means that human is at center, and the different aspects such as security, safety of human is considered whenever we have to develop any application or any device or any test bed scenario for testing the in-body, out-body, or intra-body communication. As we know, the main board is RF communication, that we use radio frequencies, but there are some associated issues with radio as well, such as one of the biggest issue is the interference, as we know that with the development of IoT and deployment of like different numerous sensors in wireless body area network, the amount of interference is going to be increased. And another aspect is the spectrum congestion, like with so many devices being used around human, the number of devices is increasing day by day, the spectrum congestion and ultimately spectrum crunch could result. So here we have this picture on our right side, which shows the concept of our paper, where we have presented that different on body, in body, and at body communication can be possible when using light as a communication mode. Light has one of its key property that it does not interfere with RF, so it can be used as a complementary approach to transmit data wirelessly. Okay. Now here we have presented the all three modes of communication, and a comparison has been drawn on in between all these three modes. So far we have been using radio communication almost like everywhere in wireless in healthcare. and when we have to transmit data wirelessly. So we have certain benefits, such as like it can penetrate better in through the body or within or in the tissue. It can the RF provides better data rates, and there are certain bands that have been allocated specifically for radio communication in in wireless body area network. And some of these are bands are narrow band and the ultra wideband. So we will focus here on ultra wideband because we have tested ultra wideband for this study. Then the acoustic communication, ultrasound, we have seen ultrasound a lot in healthcare, where it has been used to get the inside images, like different to detect the pathologies in different vital organs. So far it has been used as a diagnostic and in imaging, but it has a great potential for in-body communication, since it can transmit information wirelessly, and it can go up to 10 centimeter. Studies have shown that it can go up to 10 centimeter deep, and it can transmit data up to 10 centimeters between that. And then finally we have this optical communication. So far we have been using this optical communication for light for therapeutic and diagnostic purposes, but we haven't seen in medical application that light has been used to transmit data wirelessly. But it has like several different aspects which makes it like more favorable for optical communication, and optical communication, and for the future optical communication networks, such as like it have in light we have large and unregulated spectrum that hasn't been used. So we can make use of this spectrum, and it gives a high security, data security and safety, since light cannot be hacked remotely. One has to come in contact directly with light in order to hack the information. Okay, moving on, that we have presented a comparison statistics comparison between all three modes. We need at least 20 kilobits per second data rate for medical applications. So based on that, we have compared the different data rate that has been studied so far, or acquired so far in studies from all of these. So radio provides the best data rates among all of them, and the distances, the depth is maximum. The maximum depth covered by acoustic, but the other things, such as like complexity, security, and this security and safety, when we compare these aspects, we find this optical has upper hand in these aspects. Like optical is safe because there is no radio exposures. Even in when we are talking when we are testing acoustic, we cannot we have to have a certain limit, because we must have to follow certain limits, because we cannot expose more high powers sound waves, because it can damage it can provide damage to the body. So finally, the standards. So far we have IEEE standard for ultra wideband, but we do not have any standard yet for acoustic and optical. So we have here our experimental test bed we have constructed for this study. So on the left we have a block diagram where we show the unidirectional communication. Light from left passes through this biotissue, and this transmitted light is then captured on the right side, and then post processed and then presented in the presentation or presentable form. So we have generated a baseband signal, which is then biased with 0 to 3 volt to modulate this LED. The LED then exposes this biotissues, and the transmitted light through biotissues is captured on the right side, which is then post processed and presented on the screen, which in our case we transmitted a couple of images and through this biotissues, and we received on the other side. And we received on the other side. So, and on the right side we have this actual implementation we have done in our lab. We had this near infrared LED from Thor Labs, and then piece of meat, pork meat in between. So we have tested different depth and different sizes. On the other side of this meat we have this receiver, so it is also from Thor Labs, so which receives this light, transmitted light, and then sends it to the PC for post processing. In this slide we have presented our ultra wideband communication setup, where we used this vector network analyzer and this piece of meat, and there were one on body and one in body antennas for communication. So we have tested a big chunk of meat, like around 20 by 20 centimeter, just to avoid this RF to escape from the edges. So this piece of meat is then placed in absorber, and and the communication parameters are then drawn to find the success of the communication. So here we have presented some results from optical communication. So we have tested two different types of meat. One is the cold meat or meat at the room temperature, which we bought from the market, and we measured the temperature was around 12 degree centigrade, but the actual temperature or close to temperature body temperature is 37. So we heated our meat up to 37 degree just to mimic the alive meat without any blood. And we tested these two meats, and we found that when we heated a meat, we received more power, which means that the meat at 37 degree, which is the nominal temperature for a body, can transmit better light, and we can even go further beyond 3 centimeter in this heated meat compared to the meat at room temperature, or when we have this dead tissues. On the other hand, we have found the same phenomena when we tested these two meats, the cold meat and the heated meat, with our radio. When we transmitted, we found the same change in power loss. Like we had this higher power loss in cold meat in comparison to heated meat, where we get the lower power loss, and the power loss increases in the higher frequencies. So finally, we conclude that in this study we have compared these two technologies and tested porcine tissues at different temperatures, and find out that the similar kind of phenomena, that the power loss is more in cold meat or dead tissues, ex vivo dead tissues, in comparison to the communication where we have heated the meat up to the temperature of a body. So but there are certain benefits in RF which we cannot find in optical. One is that that the RF can propagate deeper inside tissue in comparison to optical, which has only which can only, so far at the moment, it can only go up to 4 centimeter. The power loss with optical is minor compared to ultra wideband, where we found the more power losses. Benefit of optical communication over ultra wideband is that the ultra wideband needs two antennas, but in optical we can make a smaller chipset, the since the it does not require antennas, and the other thing, it does not require two antennas. A simple transmitter and a receiver can work better. So there could we can use this light in many application in medical ICT, such as like communication with implants, and even like on-body communication, and even wireless body area networks communications, since it does not interfere with radio frequencies. So it provides a, a better solution to avoid radios, and to secure data, and to give security to the user. Thank you. If you have any question, please ask.
Hello everyone, my name is Mariela Sarestaniemi. I'm from Center for Wireless Communications, University of Oulu, Finland. And now I'm going to give you a presentation on the ultra-wideband in-body propagation meat measurements using pork meat. Here you can see the outline of my presentation. First, introduction. I explain you some motivation and aims for this work. I explain you study case, the simulation and measurement setups, then simulation results, measurement results, and finally some summary and conclusions. As you know, implant communications has aroused interest recently. One good example case is capsule endoscope, which provides reliable, patient-friendly way to examine gastrointestinal tract smoothly. But when we are designing this kind of implant communication systems, it is essential to have deep knowledge on the signal propagation within the tissues. And these channel characteristics can be studied with electromagnetic simulations, which are based on solving Maxwell's equations, or with measurements using phantom models, or with living animals which are anesthetized, or with tissues of the animals. The most feasible way is to use these measurements with meat pieces, and it is quite common way to do it. However, there are some restrictions related to the meat measurements. For example, as you know, the dielectric properties of pig resembles dielectric properties of human, but still there are quite significant differences. Also, dielectric properties of meat change as the time passes from the death of the animal. These dielectric properties are also temperature dependent, which should be taken into account when we are doing the measurements. And also, exploiting the multipath propagation environment is not possible when we have this kind of layered meat pieces. It is actually same as we compare simulation results between the voxel model and the layer model. We have three aims for this study. The first aim is to investigate by simulations the propagation differences between the human and pork tissue layer models. The second aim is to study propagation using different types of the pork meat piece having different fat and muscle compositions. Third aim is to study impact of the temperature on the channel characteristics by the measurements. First, the study case and the simulations. In this study, we used two antennas. One cavity-packed on-body antenna designed for in-body communications for 3.75 to 4.25 GHz, and omnidirectional loop antenna, which is resembling the in-body antenna in this case, although it is originally designed for on-body communications. But since it is also omnidirectional, we consider it suitable here in these simulations. And then we have this kind of layer model with skin, outer fat, muscle, and inner fat layers. Measurements. We had two different types of meat pieces in the measurements. Meat 1, in this upper figure, where the fat and muscle layers are interlaced. And in meat 2, there is distinct fat and muscle layers. And here in this table, you can see the thicknesses of these different tissues in these meat pieces. Both are 3 centimeters thick. The measurements were conducted with vector network analyzer so that these meat pieces were set individually inside the Q-form area made by absorber pieces so that we avoid signal interference from the surrounding environment, and also we can minimize the propagation overflow from the side of the meat pieces. The meat piece was set inside a thin plastic bag so that we protect the antennas and these absorbers. And here you can see the pictures of this measurement setup. So now the simulation-based antenna verifications. The aim of this study is to verify usability of this loop antenna on the measurement-based in-body propagation studies. And this verification is conducted by comparing simulated channel characteristics obtained using an implant antenna, real implant antenna, or actually this kind of capsule endoscope antenna, and this loop antenna, this on-body antenna we had here, the figure before. And the reason for this comparison is that we didn't have prototype of this kind of implant antenna. So we were considering that this loop antenna is suitable also. But here we saw the verifications that it is really possible. So this figure presents comparison in frequency and time domain channel characteristics obtained using this loop antenna and this implant antenna. And as you can see, the path loss difference is minor within the frequency range of interest. So from this 3.75 to 4.25 gigahertz, and also in the time domain. Then about the simulation-based comparison between the channel characteristics obtained using human and pork tissues. So, as you know, the dielectric properties of human and pork tissues are quite similar. However, the challenge there is that there is still huge variation in the dielectric properties which have been presented for the pork in the literature. And the reason for that is that there are several factors affecting dielectric properties of the peak. For example, the age and size of the peak, and also time from the death of the peak, and also the temperature of the meat. First, the antenna matching is studied with human and pork tissues in this case. So it is found that the difference between the dielectric properties of human and pork tissues can cause approximately 3 decibel difference in antenna notch area. So that S11 values are slightly higher with the human tissues. And the same phenomenon can be found with both antennas. And then we present here the frequency and time domain channel characteristics obtained using the human tissues and pork tissues in the layer models. So as you can see here, in the frequency range of interest, the path loss is clearly higher with the human tissues than with the pork tissues. From the lower frequencies, it is actually vice versa, but we don't have to care about those results because the antennas are not really working there. So we are now observing just this antenna range of interest. And in time domain, we can clearly see that this impulse response peak is something 3 decibels higher, at least this main peak. On the side peak, the difference is minor. So here we can see that although these dielectric properties of pig tissue resembles dielectric properties of human tissue, there's still some differences which cause something 3 decibel difference on the results. But it's okay as long as we know it. So now we are moving to these measurement results where we have this comparison between the different meat pieces and impact of the temperature. And first this comparison between the different meat pieces. So here the aim is to compare S11, S22 and S21 parameters and also time domain channel characteristics using this meat 1 and meat 2 pieces. And as you remember, this meat 1 was the meat where the fat and muscle layers were interlaced, and meat 2 had separated fat and muscle layers. And both these meat pieces have thickness of 3 centimeters. So now our aim is to observe how this meat constitution, it means that how this fat and muscle layer have impact on the antenna and channel characteristics. And in this first slide, you can see how much it affects on the antenna reflection coefficients. Here on the left, for this loop antenna, and on the right for the on-body antenna. For this on-body antenna, the antenna reflection coefficients with meat 1 and meat 2 pieces are very similar because they both are located above the skin, and this thickness of the skin and also the outer fat thickness are quite similar in both meats. So there is not too much difference. But for this loop antenna case, which is like located below these meat pieces, there is much more difference. And this difference is basically due to the fact that there is more fat on the inner surface of meat 1, whereas more muscle on the inner face of meat 2. So the antenna behaves a little bit different if it's located close to the fat or close to the muscle. And next we move to this channel characteristics comparison obtained using meat 1 and meat 2. Here on the left is the frequency domain and on the right time domain channel characteristics. So as we can see on the antennas, on-body antennas operational frequency range, the level difference is at highest 10 decibels, except exactly at 3.75 gigahertz, where there is this kind of large notch with meat 1. We didn't find the reason for that large notch, why it occurred exactly there. It needs to be studied further. In time domain, the main difference is observed in the level and width of the main peak. And here also the difference is like 10 decibels. These differences in the channel characteristics obtained using meat 1 and meat 2 are partly explained by the differences in the antenna matching. However, the main difference comes from the fact that these propagation paths are different due to this different tissue composition. Perhaps you remember that fat is known to be one of the easiest tissue for signal propagation in terms of propagation time and power loss. And that's why this meat 1, which have these kind of fat channels through the muscle layers, seems to be like easier meat piece for the propagation. So these kind of fat channels really have strong impact on the propagation characteristics. Finally, we study the impact of the temperature. Finally, summary and conclusions. We had 3 aims in this study. We wanted to investigate by simulations the propagation differences between the human and pork tissues with this layer model. And the simulation results showed clear differences between the channel characteristics obtained using these human and pork tissues within the frequency range of interest. So in this case, from 3.75 to 4.25 gigahertz, the path loss difference was up to 5 decibels. The second aim of this paper was to study by measurements the propagation using different types of pork meat pieces having different fat and muscle compositions. And we found that path loss is clearly higher with pork meat having separate skin, fat and muscle layers compared to the pork meat having interlaced fat and muscle layers. And the third aim was to study impact of the temperature of the meat at 12 degrees of Celsius and 37 degrees of Celsius. And there the difference was observed in path loss, so that within the frequency range of interest, the path loss was maximum 5 decibels, lower with the meat at 37 degrees than with the colder meat. So, use of these pork meat pieces in the in-body propagation studies has several shortcomings and restrictions. So, although we know that the dielectric properties of pork tissues resemble best the dielectric properties of human, there's still significant differences. And that one challenge is that even pork size and age have impact on the dielectric properties. And also this meat constitution has a strong impact. So if we have this kind of interlaced or separated fat and muscle layers, so it is really important that we select suitable meat piece for our measurement. And then the temperature has clear impact. We need to heat it up until the 37 degrees if we want to have more realistic results. And also one thing what has to be taken into account is that overflow from the side of the meat piece need to be minimized. So we should use as large meat pieces as possible, or then we should surround the meat piece with absorber pieces. So as a conclusion, we can say that this meat piece provide important knowledge on this in-body signal propagation, but there's restrictions in its use for these studies, and they need to be taken into account when we are doing these measurements. Thank you for your interests. Hello everyone, my name is Mariela Sarastoniemi. I'm from Center for Wireless Communications, University of Oulu, Finland. Now I'm going to give you a presentation on the detection of brain hemorrhage in white matter using analysis of radio channel characteristics. Here you can see the outline, first introduction, the study case, some power flow analysis, power calculations, channel characteristics evaluations, and finally summary and conclusions. As you know, brain hemorrhage and stroke is a fatal physical condition which may cause severe disability or even death. And that's why it is essential to be diagnosed in its early phase. And these current methods for detecting hemorrhage and stroke is practically limited on the computed tomography or the magnetic resonance imaging. And these methods are expensive and complex techniques, and basically they can be used only in the central hospitals. So there is a strong need for portable brain hemorrhage detection system which could be used outside the hospitals, for example already in the ambulance. This way we could improve the prospects of the cure of the medical if the medical treatment could be started immediately. There's been active research on brain hemorrhage and stroke detection, and they are based on different approaches. One thing what is missing is the lack of studies presenting radio channel characteristic-based brain hemorrhage detection, which would have been conducted using realistic voxel models and directive antennas. And besides, there is lack of studies presenting brain hemorrhage detection in white matter. So our study focused on detecting brain hemorrhage in the white matter in the middle part of the brain, since it is really considered the most challenging part for the hemorrhage detection. This hemorrhage detection could be done by using a simple portable helmet type of monitoring device in which several transmitter and receiver antennas could be located inside the helmet. The diagnosis could be done by setting the helmet in the patient's head and measuring and analyzing the radio channel characteristics. And the physical phenomenon behind this proposed technique is that blood has very different dielectric properties than the brain matter, both gray and white matters. As you can see here from this table, the next page. So here you can see that the blood, the relative permittivity values and conductivity values for blood and brain's white and gray matter, they change significantly for this 1, 2, and 4 gigahertz, for example, but that's valid also for other frequency ranges. So, because that's so different, the blood area inside the brain can change propagation and channel characteristics between the transmitter-receiver antenna significantly when these antennas are located in different sides of the head. The propagation losses in the tissues are relatively high, and that's why we would need this kind of strongly directive antennas for this study case, so that this received signal can be on the level in which the changes caused by hemorrhage can be really detected. So our aim in this study is to show how this brain hemorrhage with different size and different locations can be detected using this kind of directive antennas. We will show that even hemorrhages in the middle of the white matter can be detected with this method. We will show this kind of two-dimensional power flow illustrations. We can show how actually the blood really changed the propagation inside the brain. And we will also show power values at different locations inside the brain of the voxel model. And this way we can really show how it actually changed the propagation inside. And also we will show some analytical power loss calculations to confirm this difference between the hemorrhage case and the reference case. So now about this study case. In this study we used directive on-body antenna. It's biomassed matched mini horn antenna, which is composed of water-filled holes, which mimic the frequency-dependent relative permittivity, and it makes like better match for the since it's attached on the skin. Here you can see the S11 parameter for this antenna, so you can see that it works from 1.7 until 3.4 more or less, but also here a little bit higher. We used two different simulation models in this study: a spherical tissue layer model, which is full sphere, which consists of several different nested tissues, and CST's anatomical Hugo voxel model. Simulation models. We used two different simulation models: a spherical tissue layer model, which is a full sphere. Here it's just cut it for the visuality, which consists of several different nested tissue spheres, each layer having realistic thicknesses. And then we had CST's anatomical Hugo voxel model, and we chose Hugo because it has detailed brain model with separate gray and white matters with realistic shapes. In this study case, the antennas were located on the skin in the middle of the head, as you can see here in these figures. There are the crosscuts of these different simulation models. And we chose this, this part of the head because the muscle layer is thickest here, and also the head is thickest in that part. The diameter of voxel model's head here is something 16 centimeters. And this way we also designed the spherical model that is 16 centimeters here. So the possibility to detect brain hemorrhage is studied by inserting blood pieces of different sizes in the voxel model's brain white matter, and also these spherical models. The blood pieces and their locations are presented here in this figure. With the spherical model, we evaluated only the largest piece in two locations, here in the middle and here, which is partially on the gray matter. And for the voxel model, we evaluated large, medium and small pieces, all of them which are here in the middle of the brain, in the white matter. And here in the table you can see the dimensions of these blood areas we chose for this study. So now about this power flow analysis. This power flow representations are very good to describe how the blood area in the brain changes the signal propagation. And this power flow representation is illustrated here at 1.7 gigahertz. In this upper case, where is the hemorrhage, and the lower figure is the reference case. The plotted decibel range for the power flow presentation is from 0 to minus 65 decibels, where this reference value 0 decibels is set to the antenna. And the power flow on the skin is minus 26 decibels. In the presence of hemorrhage, the power flow is narrower, as you can see from this figure. Within the plotted decibel range, this receiver antenna is achieved easily in the reference case, whereas in the case of hemorrhage, RX antenna is hardly achieved. As you can see, here is a little bit gap in this power flow, but here it goes directly to the antenna. So that blood area, which is here in the middle of the brain, really has impact on this channel. The differences in power flows is due to the differences between the dielectric properties of blood and brain tissues. And as I said, blood has clearly higher permittivity, relative permittivity, than the brain matters, gray and white both, and that's why the power loss is larger in the presence of hemorrhage. here in table 3, we present a comparison between the power loss values obtained with the reference model and the hemorrhage models in the locations A, B, C, D, and E, which are described here in the app. And as you can see here, basically in most of the cases, the power is lower in the case of hemorrhage. But interestingly, in location D, so inside that brain area, it is same in this case. And also here in this C case, it's actually vice versa. So why it is? This is just one crosscut of the voxels model head. We should study more in detail also crosscut in the vertical direction to understand how actually those brain areas are. As you can see, even differences between this brain gray matter and white matter, there's quite large difference in the permittivity values. So it depends also on the structure in the vertical direction. What is reason for this? So this we have left for future study. We will describe it in next publication. And then as a comparison, we calculated power loss with MATLAB based on this kind of planar model propagation. And this calculation utilized extension of algorithm that is included lossy media proposed by Orphanis in this reference 16, you can see from the paper. Here the tissue thicknesses are calculated in the presence of large hemorrhage, and these we use these all tissues here in this calculation. You can see those relative permittivity, loss tangent values, and also the thicknesses which we used here. And we calculated it both in the reference case, so without that additional blood, and power loss with the blood. As you can see, the power loss with the blood is 59 decibels, whereas in the reference case it's 50. So there is a significant difference. Please note that this is now with the large hemorrhage model. So it is even 9 decibel difference. And this was at 1.7 gigahertz frequency. So based on these calculations, the difference between the hemorrhage case and the reference case is quite large, 9 decibels. But why then the difference was not so huge when we check the power values with that voxel model? So the reason for that is that these voxel models, they have like more complex structure, whereas these calculations were based only on this kind of layer model, planar layer model structure. So these voxel models and their complex structure enables alternative propagation path than just the direct path through the tissues. And this is the reason why the difference is milder in the voxel models case. So basically in those planar layer calculations, the signal has to go through all these layers with all those thicknesses, whereas in the voxel model case, the signal can like choose the more easier propagation path. Anyway, those powerful loss values, what we calculated analytically, provide good reference showing clearly the impact of the blood on the channel characteristics. And now we move to the channel characteristic evaluations, and first with the spherical model. So here we evaluated this spherical model in the presence and in the absence of the blood, and in these both locations, here in the middle and here a little bit crossing the gray matter as well. And here you can see the results. The reference case is this black dotted line here, and here blue line is when the blood is here in the left, and the red line is when the blood is in the middle. And as you can see, the blood in the brain causes clear differences in channel characteristics, especially in this frequency range 2.5 to 4 GHz. The changes in the lower frequency range are milder. And the reason for this is that the higher the frequency, the smaller the wavelength, and this gives better resolution. So that's why the hemorrhages are easily detected there. And then channel characteristic evaluations with the voxel model. Here we did similar evaluations, but in this case the blood area was in the middle of the brain with these different sizes, SML, small, medium, large. You can see them here, the SQ1 parameter from them. Also in this case, the channel with the reference model is at higher level than channel with the hemorrhage model for most of the frequencies, as expected from these power loss calculations. Interestingly, anyway, here at 2.6 GHz, the SQ1 for the reference case is at a lower level than in the case of largest hemorrhage at the highest level. So yeah, that's interesting why it happens here. That we will study a little bit further. But it might be that because the difference on dielectric properties of blood and brain matters have variation, and it depends on the frequency. So that's why it is very important we select carefully the frequency range which are used for this technique. Here I still wanted to show the tuned version of those SQ1 parameters at the lower frequencies, here around 1 and 2 GHz, so that you can see that actually also here the difference is from 1 to 5 decibels even, so it is also clearly detectable in practical solutions. So finally, summary and conclusions. Detection of brain hemorrhage in its early phase is essential for the better prospects of cure. And if we can detect the hemorrhage or stroke with portable devices outside the hospital, it would be really essential. Blood has different dielectric properties than brain's white and gray matters, and thus additional blood areas inside the brain change the radio channel characteristics between the transmitter and receiver antennas. So our study presented in detail how these blood areas in the brain really change the propagation between transmitter and receiver antennas if they are located opposite sides of the head. These two-dimensional power flow presentations, power loss calculations, and channel characteristic evaluations all show clearly how it changed the propagation. And we could show that even small sizes of the hemorrhage can change these radio channel characteristics, and even if it's located in the middle of the white matter. But it's very important that we use directive antennas here so that we can really detect these small areas as well. The path loss difference was from half to 15 decibels between the reference and hemorrhage cases, depending on the frequency. So our future work objectives include we will study more in detail the impact of the hemorrhage in different frequencies and with several antennas to maximize the visibility of the difference. We try to find optimal antenna locations. We will study different size with different size of the head models so that we get this variation between different reference cases. And then we will also conduct radio channel measurements using a real human skull filled with phantom materials, and we will insert some blood areas there as well. Thank you for your interest.
Hello everybody, and welcome to my presentation on ultra-wideband microwave imaging for inclusions detection, where I present a methodology for comparing artifact removal algorithms. My name's James Puttock. I have done this project as part of my dissertation for my final year, so I've just graduated the BEng program in Electronic and Electrical Engineering at London South Bank University, and for this project I've been working with the PhD team, Beina Sahani, Banafshik, Khaleesi, Dr. Guizani Tabiri, Professor Sandri Dudley McAvoy, and Professor Mohammed Guizani. So just outline what I'll go through today. So I've got a brief introduction and the motivation for doing this project. I'll give a brief introduction to ultra-wideband microwave imaging. I'll then go through the artifact removal techniques that I've been comparing and the image quality index methodology that I used. I'll then briefly go over the results as well. So as a way of an introduction, hemorrhagic stroke. Hemorrhagic stroke is a bleed on the brain. This is what this project has focused on. These similar studies have already been done with regards to breast cancer detection, and we were wondering if we could use the technology to in a similar way for hemorrhagic stroke. So as I mentioned, hemorrhagic stroke is a bleed on the brain. It differs from ischemic stroke, which is when blood is restricted in the brain. So current imaging technologies are either really very large, expensive equipment, MRI scanners and the like, are very claustrophobic, or they require substantial doses of ionizing radiation in the case of CT. But also, all this equipment is very expensive and tends to be just at main hospitals that you'll get this equipment, rather than it's not very portable. It's all large, expensive equipment. So ultra-wideband, which the technology we'll be using, uses a very, as the name suggests, uses a very wide band of the frequency spectrum, which has advantage because of the high bandwidth. It's very low power compared to other techniques. It's non-ionizing. It uses the microwave region, and so it's similar to mobile phone technology in terms of the how ionizing. And it's non-invasive. You can take imaging from outside the body, not have to squish people into claustrophobic spaces or anything like that. You can create portable devices as well, because the technology doesn't require large hardware. So there's opportunity using this technology to build non-invasive, non-ionizing, portable device, and cost-effective as well, which components are relatively cheap compared to others. So there's potential here for something good to come out of this. So ultra-wideband microwave imaging. So as the paper demonstrates here, we've demonstrated that it's possible to image an object. So in this case, we've used just a cylinder, which we've done through simulation. And it's possible to image an object with an inclusion inside by transmitting microwave frequencies over a wide band and measuring the electric field around the perimeter of the cylinder. So here we have an image of a transmitter. The orange is our cylinder. The pink area is an inclusion within that cylinder, and the black is a receiver. I want to note that for our project anyway, this isn't a receiver array. It's just one receiver that we've moved for each measurement. So you measure receiver at one point, then it moves on to the next point, and so on and so forth. So if you image by summing, we've got a summing algorithm. If you that's presented in the paper. If you sum the electric field measured at these points, you get something like this, which isn't really all that helpful. And what you're seeing here is just the reflected signals of that transmitter. So the transmitter is giving off a signal, and as it goes to the other side, you're seeing this first wave come in, and this is your reflected signal that you're seeing here. So not overly helpful on its own, but if you then image a cylinder without an inclusion, so exactly the same setup as before, it's actually exactly the same cylinder, but the inclusion's been removed, you'll get something similar. If you subtract one from the other, you'll see the inclusion has actually been picked up. So it is there. Using the data, it is possible to pick up this inclusion just by measuring the electric field from outside the cylinder. Now, of course, the problem we have is when you're imaging a head or when you're imaging any part of the body, it's not possible to have a perfect medium to act as your method to subtract from. You haven't got this perfect cylinder to act as subtraction. And so we need to come up with other methods. And so each of these have varying quality and removing artifacts, which are the unwanted signals, which we'll go through now. So the technique that LSBU have been using most at the moment is average subtraction. So the way this works is you take the results from multiple antennas. So here's your transmitter and your cylinder again with the inclusion, and the points at which you're measuring around the circle with the receiver. If you take the average result, so if you use 3 transmitters and take the average result, so you take the results from transmitter 1 and put that into a matrix, you then create a second matrix for the second transmitter, a third matrix for the third, and then you take the point-to-point average across each of those matrices, and then you minus 1 from the other. And what that does is give you an image like this. So this has picked up the inclusion, which is what we want. It's also picked up a lot of these unwanted signals around the edge, which are the artifacts. And these are made up of reflections of the transmitted signal and also from the surrounding medium, it's signals that it's picked up as well. So another method that has been explored in the study is rotation subtraction. So this uses 2 transmitters placed however many degrees apart. We've used 4.5 degrees. And if you measure the electric field from one transmitter and subtract from the other, so you've got one transmitter on the left there, and we've moved the transmitter and did exactly the same experiment on the right, then that creates a table of results and gives you another method of exploring, another method of gaining results and gaining an image. Differential methods. So you don't just have to use the raw electric field measurements to produce the results. Instead of building a matrix directly from them, you can build a matrix from the difference between various receivers. So if we were to go around and take the results from receiver 1 and the results from receiver 2, the difference between them, and put that in number 1 slot in the matrix, and then you go to the second one, the difference between receiver 2 and receiver position 3, and put that in number 2 slot in the matrix, and so on and so forth all the way around the perimeter, you get the neighboring receiver type matrix. There's a similar one as well, which uses symmetrically opposite. So this takes receiver position 1 and subtracts receiver position 80, and then you do the same for position 2 and positions minus position 79, and then 3, 78, and so forth. And you put those in matrix in order as well. And so these are just 2 of the methods that we've selected from research that had proved successful. With these methods, you end up with a matrix that then needs to be put through either rotation or average subtraction methods at the end. So you do this method for either 2 transmitting positions or 3 transmitting positions, depending on whether you're using rotation or average subtraction methods, and then you do that method as before. So the symmetric receiver method that was the right-hand one on the previous slide, that is very prone to reflected signals. So because you're taking the signals from either side, you tend to get reflected signals. So if as a demonstration here, for this project, we've rotated the equipment 90 degrees. If you were to take the results from here, you'd get something similar to this. And as you can see, the inclusion has been picked up. So the inclusion's in the lower right there, the red area in the lower right. And then at the top, you've got this reflected signal, which is from where you've taken the difference across across the cylinder. So the hypothesis was, if you were to then rotate the equipment and take the difference again across symmetrically opposites, and then sum them, what you can do, you'll get an area of high intensity, which will be the area of the inclusion. That'll be at highest intensity at the area of the real inclusion. So if you did that, you can see that in the image there, in quite a small image, but you can see the image. The high intensity area there has given quite an accurate position for the inclusion. So to compare all these different images, I had to come up with a method of a valuable method, a valid method of comparison. So the image quality index is what I decided to go to do. So humans are reasonably good at comparing the quality of images. However, they are subject to bias, and I wanted to come up with a quantitative approach, something that gives a number between 0 and 1 of how good a quality the image is. So quantitative measure allows that fair comparison, and it attempts to remove the bias. So I use the ideal image method. So the imaging method we first started with, where we subtracted a cylinder without an inclusion from a cylinder with an inclusion, that perfect method. The hypothesis was that represented the best possible result we could aim to get using these techniques. And so this was used as an ideal image reference. And then each test image we then did was done in comparison with that ideal image. So we used a variety of image quality metrics for comparing images. So the mean square error takes the error value, so the matrix values of one image and the ideal test image and an ideal image. You take the error value, which is the difference between them, and then square it to eliminate any negatives, and then take an overall mean value of the matrix to give you a score of how good your how much error you have. There's the area difference. So MATLAB has some useful polyshape functions. So what we did was the results were normalized anyway, and any two between 0 and 1. And any results that were over 0.75, they were what represented the inclusion, or what we'd picked up as an inclusion. So any areas over 0.75 we assigned to 1, and everything under 0.75 we assigned to 0. So we just were left with a single shape, which, using MATLAB's polyshape and polyboundary functions, we were able to get that shape and get the area of the shape. And then we could compare the area of the ideal inclusion image with the area of the test image. The centroid difference in a similar way. So whereas the area difference measures the accuracy, the centroid difference it uses the principle of centre of mass, and as this is a similar density, because we assigned everything to 1, centre of mass will be the centre of the shape, and the centre of the shape, how much that had shifted between the ideal image, where the inclusion was actually located, and the test image, and that centroid difference then gives an indication of the precision. Signal to noise ratio. So this is used a lot, not just in imaging, but also in many fields. So this was done, and again as a comparison. So we took the signal to noise ratio for the ideal image as being the best that we could hope to achieve, and the signal to noise ratio for the test image was then done as a comparison between that. The structural similarity index metric. So this is a metric which gives us a score between 0 and 1. Based on the structural similarity, it looks for contrasts in the image, and from that it detects how the structure of the image between two different images differs, and it gives both local scores and an overall score for the image. And then the average difference is the difference between point-to-point difference on the matrix, and then the average of those differences. So I used a weighted combination of these metrics to produce an overall score for each image. So these are results. So at the result stage, every single experiment output these 6 images. So the top left is the test image. So in this case, we've used average subtraction. The top left is the average subtraction image. The top right is the ideal image that was produced using the same results. And then we also produced an error image, which is the top center, this was just given to give a visual idea of where the error lies in the image. So, and that's just the test image subtracted from the ideal image, and then we image the result. And it's just there to give a visual tool for anyone looking. The bottom left is the polyshape image, so where we took every value over 0.75, and it just shows where the area is that we've measured. So this is the area of inclusion that we've picked up in the bottom left, and the bottom right is the same image for the ideal image, the ideal reference image. And then the bottom center is the SSIM image, where the structural similarity, and what that's done is taken the local scores of SSIM throughout, and any areas of high contrast are denoted in black there. So these are the results that we have for simulations. So we ran simulations in MATLAB with inclusions at pi radians and minus pi over 4 radians. I've only presented the minus pi over 4 images here, but there's the pi ones are included in the paper. So the top row represents all of the average subtraction methods, and then the bottom row represents all of the rotation subtraction methods. And the way that each column is then taken an experimental procedure and shows the experimental procedure for that. So the first column uses average subtraction at the top and rotation subtraction at the bottom. Then the second column there, B and F, that uses the differential neighbouring receiver type with average at the top and rotation at the bottom. And in a similar way, C and G are differential symmetric receiver type. And as you see with those ones, we've actually picked up those reflected signals. With the differential neighbouring receiver, it tends to have picked up signals from around the edge of the inclusion rather than the inclusion itself. The symmetric receiver has picked up the inclusion, but it gives you a symmetric reflection. And then the sum symmetric is the final column there, the D and H images, and you can see that that's actually come out quite well with by summing the two different symmetric at 90 degrees. It's given a really clear indication of where the inclusion is. So these are our results. They are in the paper, so I won't go spend too long on them. But you can see that there's quite a big change, especially with the differential neighbouring receiver type and differential symmetric receiver type. There's quite a big difference when the inclusion position is changed. The sum symmetric receiver type has given quite high scores for both, and the average subtraction and rotation subtraction have been given reasonable scores as well. But what's nice with those as well is they haven't changed considerably. There's only 0.02, 0.03-ish a change between the two images. There's not huge jumps, but when the inclusion position changes. So as a conclusion, as I mentioned, some symmetric receiver type scored highly. The position of the inclusion can vastly influence the image quality. So this is likely because of directly reflected signals and the signals being split. It could be improved by using multiple transmitter triplets. So rather than just using 3, this method could be replicated around the perimeter, and then it would help to eliminate some of that uncertainty. This study only focused on cylindrical inclusion inside a cylinder. Further study options could change the shape and the size of the inclusion. Then it could progress onto head mimicking phantoms and simulations, and see if the results are still the same. It could also use measured results rather than just simulations. It would also be good to compare the image quality index with what knowledgeable experts think from giving a viewing of the images. So thank you. I'd just quickly like to acknowledge that our funding there, the details of which are on the screen, but also the co-authors who have helped me out throughout this project. So Bena Sahani, Banafsheh Khaliti, Dr. Guizani Tabiri, Professor Sandra Dudley-McAvoy, and Professor Mahara Gopalami, who have all worked together on this project. So thank you to everyone, and I'll be available for questions.
Hello, everyone. My name is Ming Li. I'm currently a professor of computer science at California State University, Fresno. This is a joint work between my group and Dr. Propagation at the University of Texas in Dallas. The title of the presentation is BSNCloud, Cloud-Centered Wireless Body Sensor Data Connection, Streaming, and Analytics System. So first, let's introduce the background. So the research we're doing falls into the broader area of wearable computing, which has been quite popular during the recent years. There have been quite some sensor modes available on the shelf. We can buy and use directly and connect with computer systems, tablet, phones. And also there are quite some softwares to assist the deployment such sensors. The vendors include, for example, Shimmer Sensing, Qualcomm, Intel, and Apple. We can use Apple, iPhone or iOS devices to basically do some analysis with built-in sensors. The integration with cloud server has been more of interest because cloud server provide additional computing power and storage space to assist large volume data connection and analysis. Despite of those advances, there are still two key issues we need to consider. First one is we want a user-friendly multiple sensor supported real-time and powerful analytics support for high-quality patient health monitoring activities. We know that for health monitoring, the key thing is data analytics. So we need to put this data analytics as the key part of any research so that we can support them. Another thing is biomedical researchers many times face significant challenges of high cost and overhead performing those analytics. For example, biology or medical clinical professors, they don't have usually the expertise on algorithms. They don't have the team to do the development for their own tools and the algorithms. So deployment of such system and then perform analytics usually takes months or even like a couple of years. So we actually outline some basic requirements on desired features of a good system where usability should be provided, the cost of sensors and how available are they on the shelf, and how can they handle real-time and on-demand analysis. Do they make use of cloud server to improve their efficiency? And also, can the system extend further to more mobile devices and wireless sensors? So first, let me introduce some related works. There are quite some communication technologies to support the short-range body area communications. For example, we have Zigbee. Of course, Zigbee, the range is actually higher or much higher than the body range, but it has been quite popular in supporting such network structure. The standard is 802.15.4. Bluetooth also with much wider range, also with high power, and therefore, Bluetooth low energy was proposed to make the energy consumption much lower. And the actual standard for body air network is 802.15.6. However, for now there is no commercial sensors being sold in compliance of this new standard. There have been quite some frameworks to facilitate the data analysis, data connection, data processing, streaming. One of those is called SPAN, Signal Processing in Node Environments. And Shimmer Sensing provides some tools to do the connection, log, and the plot, which are separate tools you can use. DexterNet is a research that incorporates SPAN and provide the real-time data, sensor data analysis. So, which further, improve the flexibility of the SPAN. And CodeBlue proposed to have ad hoc infrastructure by body sensors, which kind of flexible. However, body sensors, if you make a ad hoc network structure, then the performance can be an issue. Carelet proposed to integrate wireless sensors to have web portal and some other integrated environments to improve the usability and the scalability. And regarding the cloud computing integration, we have OSWA, Open Sensor Web Architecture, and the CCWSB, which combines cloud computing and wireless sensor networks. And Body Clouds was proposed to have a software as a service approach to support cloud-assisted BSN applications. And finally, we have proposed quite some work on improving the data reliability. For example, by understanding the data analysis requirements, we can have a data analysis driven adaptive framework where we can decide what to transmit to meet the reliability requirements to have a better quality analysis. We also propose to evaluate the importance of different samples by looking at how easy a sample can be estimated by other samples. We kind of calculate the contribution of reliability by different samples, and we group them together and transmit them progressively so that we can achieve a low data volume requirement for transmission and still achieve very good reliability as well as analysis. And also we propose a loss resilience transmission scheme to adaptively, adaptively control the sampling rate so that we can make sure, the performance quality of service can be provided. So this is the system architecture for a typical wireless body air networks. We have a patient with various sensors from ECG, EEG, and blood pressure, motion accelerometers, and so on. And those sensors wireless communicates with phones or tablets or laptops through either Bluetooth or other like a Zigbee communication, and then the access points and the phones, tablets are through Wi-Fi, and then we have a cloud server in the internet. So in this case, we have an integrated network architecture. So what we proposed is called the BSNCloud. So this is a cloud-centered system for biomedical body sensor data connection, analysis, streaming, and storage. So we propose to have both data repository and algorithm repository at the cloud server. We can support real-time and also on-demand analysis. So for our system, we actually have a very not too big fat, but a very function-rich data aggregator, which can do sensor control, data presentation, event detection, and data analysis and data communication. So here I want to point out that so we do support the real-time analysis at the data aggregator, which can be Android app, which uses an Android app. The Android app actually can do visualization, data connection, also do some statistics, and then stream data to the server for backup or request a real-time analysis. We use WebSockets to communicate with the server. For the cloud server, we actually have a data repository and algorithm repository. So we designed a machine learning engine so that a user can use our web portal to submit a request for analysis or upload the algorithms, upload the data set. And then the web service, the machine where the machine engine is located, can perform various functions, including performing on-demand analysis, including performing real-time analysis through the Android app. And once the result is generated, so it will send back to either the Android app or the web portal, so that user can immediately see the results. So we designed a system with 5 server cloud cluster with 1 master and 4 slaves. So every server has 2 by 8 core Intel Xeon processor, and the total storage space is over 40 terabytes. The operating system we use is Ubuntu, and then we install Open Stack on top of it. And then we have a web server based on XAMPP Apache PHP. So the sensors we use is from Shimmer Sensing, the Shimmer 3 IMU, which has a very small dimmering, and with 24 MHz MSP 430 CPU. It has very low power consumption. It provides 5 colored LEDs to indicate the operating and monitoring of the sensor. And SD card of this sensor can provide up to 7 gigabytes volume. And it supports Bluetooth only. And we have it has non-DOF inertial sensing through various sensors. So basically, one reason we choose Shimmer is, the Zigbee sensors we usually use, those TEL OSB, the vendors no longer produce those. So Shimmer even decided not to support Zigbee. So right now it's only Bluetooth, which is good because most iOS devices and other devices, they all support Bluetooth. So Bluetooth is more universal from this aspect. And also those data are highly accurate and scientifically reliable, which is perfect for medical applications. So we develop an Android app. So here we can see we can enable a variety of different sensors. We can we also have a function to do event detection, statistics, stream, store data. When the phone is offline, we can perform user analysis and real-time analysis. So here we can see the further configuration for the Android app. And we can have data visualization. This is from the Shimmer, the basic multiple sensor templates. So here we can see, user can send a request for real-time analysis of the most recent connected data. And then the analysis result can be received in real time. At the web portal site, we have a very nice user-friendly web page to allow users to submit data sets for sensors, and also they can upload data algorithms. So if they want to perform analysis, they can choose sensors, algorithms, and the data sets. And then the system will show a summary of what they choose, and then they can run the test. So here are the experimental results. So we vary different sampling rates and find out the throughput remains consistent. So which is nice. So that means the app is functioning stably. We also look at the different the real-time analysis response time with different kinds of data. So we can see the real-time analysis response time is roughly about between 4 seconds to 6 seconds. So average about 5 seconds, which is acceptable. And we also look at web portal data analysis response time. We vary the data size. So we can see here with different sizes, small to high. The high can be about 25 megabytes. So we can see the response time is quite nice, which is actually lower than the Android app real-time analysis, because the cloud server connects with the web portal. The delay is relatively less compared with the wireless communication between the phone and the server. So in summary, we actually propose Body Sensor Network Cloud. Is a cloud center system for biomedical body sensor data connection, analysis, streaming, and storage. The key design decisions were made to maximize usability, efficiency, and scalability. We aim at facilitate the data analysis research and significantly reduce the cost and overhead by researchers. So this system has the potential to grow with active use and contribution from the research community. So finally, I want to thank National Science Foundation of USA to support this research. I thank the audience for watching this video. If you have any question, you can contact me with my email address.
Hi everybody, my name is Leonidas Chapoulos from Tallinn University of Technology, Estonia, and I'm going to talk about our work on model-based analysis of secure and patient-dependent pacemaker remote monitoring system. The importance of permanent pacemakers has been very, very high. The embrace of sensors and advances in communication and cloud technology has enabled us to develop effective monitoring applications in different areas, including the health sector. Cardiac implanted electronic devices such as permanent pacemakers exceed 500 units per million inhabitants worldwide, and this number is increasing. So, remote monitoring of pacemakers has improved the patient survival rate, according to recent studies. But still, for such deployment rate, the reliability and operational lifetime of pacemakers is an important factor to prevent fatalities. Pacemaker data communication is important for device adjustments, but also it is very important for episode alerting, so the clinician knows what is happening with their patients. Due to high energy consumption of wireless communication, frequent data transmissions of pacemakers were not possible in recent times. Energy efficient Bluetooth low energy connected pacemakers were introduced in the market just recently in 2016. But still, the impact of wireless communication to device energy consumption is very remarkable. It is important to optimize wireless communication frequency and data amount to be transmitted, heavily depending on patients' clinical needs. And although patient monitoring quality has vastly improved, but it also added security risks, the monitoring itself. The range of security threats gets very wide because many nodes take part in the communication, from pacemaker device itself to the mobile phone to the cloud. There are many nodes in between that they increase the range of the threats. It is essential to establish end-to-end security that covers the whole communication medium, and the security countermeasures create an additional burden to security constrained devices because they imply additional energy consumption. So there is a strong need for lightweight and multi-level security countermeasures applied according to the patient's active environment. To reduce threats and possibly infeasible design decisions, we propose a model-based formal analysis for design and runtime configuration decisions. We take into account the effects of pacemaker remote monitoring and secured episode alerting to the device lifetime, depending on the different patient profiles and security countermeasures adjusted to daily living environment. We perform probabilistic modeling, simulation experiments, and model checking with UPAL time automata to estimate the impact of various factors to pacemaker expected lifetime. Some preliminaries for UPAL time automata. So they are usually a composition of processes, and processes consist of location and edges, as we see on the left side of the slide. We see three locations connected with three edges. So with the computations of the model, there are clock variables and also integer data variables. We have clock resets, and then we have clock invariants and clock guards, specifying the bounds for when the next outgoing transition can be executed from action towards the post location. And we have synchronous parallel composition between processes, and this composition is implemented with synchronizing channels. On the right side of this picture, we see the in and out channels. More we will see with the model soon. The query language of UPAL is used to specify properties to be model checked. It is a subset of time computational tree logic. We can have state formulae for properties interpreted in individual states, and path formulae that quantify over paths of the model. And these path formulae are classified into reachability, safety, and liveness properties checking. For this work, we consider only the checking of safety properties. The view here on the right of the slide, it shows what this formula expresses. That formula phi should always hold on all stages of the model. For this work, we consider three different patient profiles. We have the best case patient profile, that he is away from home 10 hours per day. So 14 hours per day he is at home. He's visiting the hospital only once per year, and this visit is only 2 hours long. he has only one dynamic alert per year in any of the 3 possible environments that he can be. The medium case patient profile is about a patient that he's away from home 6 hours per day, so 18 hours per day he's at home, and he's visiting the hospital two times per year, and each visit is 4 hours long. And he has 4 dynamic alerts per year in any of the 3 environments. The worst case patient is much different than the other 2 patients. So he's away from home only 1 hour per day, 23 hours per day he's at home. He's visiting the hospital 4 times per year, and each visit is 2 days long. He has 10 dynamic alerts per day in any of the 3 possible environments. What about the countermeasures, security countermeasures we consider? So we consider configuration 1, which is about datagram transport layer security session resumption with advanced encryption standard. Yes. And for this configuration, we have trust to the gateway in the hospital. So this configuration is suitable for the hospital setting, for the hospital environment. Configuration 2 is about a symmetric key-based DTLS, and there is no trust to the home gateway. That is why it has to be stronger than configuration 1. And sharing of symmetric key rather than the certificate in this configuration. Configuration 3 is the heaviest one. It's a certificate-based DTLS, and it provides more assurance for the device authentication in non-stationary places when the patient is traveling. So, network and energy considerations for this security options we have. We have end-to-end security from sensors to the cloud. The gateway is transferred only in configuration 1 in the hospital setting. The benchmarking results from about energy consumption, we took them from the publication that can be seen in the lower part of this slide. And based on this work, we have that the configuration 1 is less costly than configuration 2. The cost is 1/6 less. And configuration 3 is 32 times more costly than configuration 2. Also, we consider that the handshake happens for each data alert transmission, and the energy consumption is dependent on the handshake. So, some words now for the alerting cost for the pacemaker model that we will see that we have developed. The pacemaker device battery lifetime is 5,000 days, and this can be taken from the manual of the Medtronic pacemaker. We assume that daily reporting from home, only from home, is active for all patients, and this reduces battery lifetime by 564 days. So after some calculations, we have that 189 daily reporting sessions reduce battery lifetime by 1 day. The dynamic alerts have different costs on battery lifetime, depending on which of the 3 environments a patient is when the alert is triggered, and this is due to the different security countermeasures applied in the different environments. So the dynamic alert from home costs the same as a daily report. This is one assumption we have also additionally. The dynamic alert from hospital costs 1/6 less than from home, so there have to be 220 hospital alerting sessions to reduce battery lifetime by 1 day. The dynamic alert when traveling costs 32 times more than the alert from home, so 6 travel alerting sessions reduce battery lifetime by 1 day. And this correspond fully to the cost of the security countermeasures we assume, we take into account. And here we see the model declarations, the UPAL model declarations. P is the patient type index with domain 0, 1, 2. N is the number of patient profile types, 0 for best, N for medium, and 2 for worst. M is the normalization to 1000 of the probability weight in order to accommodate all model probability weights into approximating integer scale from 0 to 1000. On this scale, pH denotes the probability weight of being at home any hour around the clock. PT the probability weight of traveling. PV the probability weight of visiting the hospital. PR is a daily probability weight for the daily reporting and is the same for all the patients. That's why the number is the same in the curly brackets. PA is the probability weight of alerting at any hour. A variable env is for the environment the patient is currently located in and can be assigned symbolic values home, travel, hospital. And the variable lifetime expresses the battery lifetime estimate in days and is calculated iteratively in every model hour depending on different environment communication events occurring with specified probabilities. and the initial value is 5,000 days when the battery is full. Constants with a delta word part of their name is it's constants showing the decrease of battery lifetime by 1 day after the amount of daily reports or alerting is necessary to occur, and they're related to the variable CRD, CRO, CRT, and CRH, standing for counter variables for daily reports and for alerting from home and alerting when traveling. And when these counter variables reach the constants we see on the last line on the right side of this figure, then there is a decrease of lifetime by 1 day, and these values are reset and they're incremented again. And now we see the patient and hour clock UPAL templates model, and the state updates are triggered every 1 hour with sync channel CHH from the hour clock template. And the automaton patient models possible moves of the patient between environments. The initial location is his home on the left side, and with probability PH it is indicated that he stays at home, and probability M minus PH indicates that he is traveling. Probability PT indicates that he keeps traveling, while probability PV indicates that he will visit the hospital, and probability M minus PT minus PV indicates that he will return back home. The value vectors of the probabilities are as given on the previous slide, and the elements of vectors correspond to different patient profiles 0, 1, and 2 for best, medium, and worst. A concrete element is chosen from vectors PH, PT, PV, and PA, depending on what value of patient template parameter P is selected for the model experiment. Variable env for environment is updated according to the patient location in the current state, and location value affects the type of dynamic alerts, which in turn affect differently the battery lifetime. And this affection can be seen on the next slide, where we see now the UPAL device model, UPAL template for the device, for the pacemaker device. And there are two main locations in this template, one for monitoring, regular monitoring, and the other for alerting. From monitoring with probability PR, daily reporting occurs, and whenever variable CRD reaches constant value CD, according to the amount of reports needed, then the battery lifetime is decreased by constant delta LTN. From monitoring with probability M minus PR, daily reporting does not occur. During monitoring, dynamic episode alerting occurs with probability PA, being different for each patient profile, as we saw earlier. And battery lifetime is decreased depending on the environment the patient is currently located. And this is shown on the upper part of this template, and with regards on the environment values. Since the minimum time step in the model is 1 hour, sub-hour activities timing is ignored and modeled just using committed locations. And they are the locations seen with a capital C letter in the middle of them, in the nodes. Committed locations, they do not allow time to progress, so all these updates we see here in this model, they are instantaneous, they're atomic. So what can we model check on this model? So this model allows for checking critical battery lifetime properties depending on the different patient profiles and patient activities. We can check that the expected lifetime is safe, so meaning that the battery level never gets below a critical value before planned replacement time. And this is 15% of its initial level. If nominal lifetime is 5,000 days and the depletion rate is constant, the critical threshold will be reached by 4,250 days. So the query that we see on the slide expresses that in all states of all possible scenarios within the closed time interval from 0 to 4,250 days, the calculated battery level will never get less than the critical value, which is 750 days remaining battery life. On this table, now we can have a look at some at the simulated data from the model. The table shows the results of for all three patient profiles we consider. We have the different colors for the grouping differently. What is happening, what is the cost of alerts, and the depletion of battery in days. We have the red color, violet color, and blue color to differentiate that. And so what, as can be seen, the pacemaker expected lifetime estimates for patient type 0 and 2 differ a lot, and having common rough estimate regardless of the specifics of patient profile is a big risk to patient safety. And frequency of alerting and security protocols used in different environments that have substantial effect on pacemaker expected lifetime. And on the lower part of the table we can see that with bold number what is the lifetime of the device battery for each of these different patients. Patient type 0 and type 1, they are close, so their battery will be depleted completely after 4,400 something days, 35 and 31 correspondingly. But the patient profile type 2 is much worse, so his battery will last only for 1,239 days. And the lifetime till expected, the lifetime of the battery till the 15% threshold that we saw earlier in the previous slide, we see the number for each of these patient profiles in the lowest row of the table. But what about going back to the query that we wanted to model check for all different patients that we consider? Is this query satisfiable for any patient profile? At first, one could think that it's satisfiable for type 0 and type 1 patient, but no, actually it is not even satisfied for them. It's not satisfiable for any of the patient profiles we have in this model. And this is because of that if something more than the daily reporting is taken into account, so we have to reconsider differently also the parameters and some other and lifetime and the energy consumptions. So the conclusions for this work. We have presented a model-based quantitative analysis of pacemaker lifetime that takes into account patient-specific factors, including general health condition, acting environment, remote dynamic reporting of vital patient data, and alternative security protection measures for these data communications. Instead of supporting only a single security model, we proposed a multi-level security model that allows to select different security levels for better protection in the different patient active environments. We performed probabilistic modeling and model analysis with Opal time automata on a fully parameterizable model regarding patient profiles focusing on pacemaker operational lifetime prediction. This model can be adjusted in various ways, can be instantiated through the parameters and variables in many ways. The approach to fine-grained battery lifetime analysis using probabilistic time models is flexible because it can easily be adjusted by incorporating in the model only the factors that have impact to device endurance and reliable maintenance planning. This is our main statement after this work. So, thank you. Any questions?
Hello, I'm Max from the Institute for Electronics Engineering at the Friedrich Alexander University in Erlangen. As I will show in this presentation, we successfully applied amplitude modulation using a micropump in a molecular communication testbed with superparamagnetic iron oxide nanoparticles. In areas where conventional wired or wireless transmissions are not feasible, for example due to a high level of miniaturization or safety concerns, molecular communication can provide an alternative solution. In molecular communication, either molecules or synthetic particles in the nanometer range are used as information carriers in mostly air-based or fluid transmission channels. Some examples from experimental setups are air-based transmission using alcohol or the modulation of pH value in a fluid environment. To investigate a molecular communication setup using superparamagnetic iron oxide nanoparticles, spions for short, a testbed using a fluid transmission channel was developed previously. We now improve this testbed using a micropump for spion injection to facilitate amplitude modulated data transmission. In the course of this presentation, I will first outline the individual components of the testbed setup, then I will describe the methods applied to achieve data transmission and show you the results we accomplished. I will end the talk with a short conclusion and an outlook on future work. In our testbed, we used spions as information carriers. These are iron nanoparticles that have a high susceptibility and no remnants due to their superparamagnetic properties. Our particles were synthesized by the Section for Experimental Oncology and Nanomedicine of the University Hospital Erlangen. They have a hydrodynamic radius of approximately 50 nanometers and are coated with lauric acid. As they are biocompatible, there are many possible use cases for spions. The transmission channel consists of tubing with an inner diameter of 1.52 millimeters. A constant background flow of water with a flow rate of 10 milliliters per minute is provided by a peristaltic pump. Spions are injected into the channel using a venous cannula with a diameter of 0.8 millimeters and a pump. The injected particles travel in the background flow to a receiver where they are detected due to their magnetic properties. The distance from the point of injection to the receiver is 5 centimeters. Information is encoded by varying the particle concentration in the transmission channel over time using coded bursts. In previous work, we used a peristaltic pump to control particle injection. However, this device was big, imprecise, and was operated at a fixed injection volume. In a step towards miniaturization and improvement of data transmission inside the testbed, we replaced the peristaltic pump with a steel micropump. This pump was manufactured by the Fraunhofer Research Institution for Microsystems and Solid-State Technologies in Munich. The pump uses a piezoelectric actuator, has a diameter of 20 millimeters, and can move a volume of 11.5 microliters per pump stroke. By changing the voltage applied to the piezoelectric actuator, pump strokes with a reduced volume can be performed. In these three diagrams, you can see the different actuation states of the micropump. At the top, you can see the first state when no voltage is applied to the piezoelectric actuator. The inlet and outlet valves are closed, and the pump chamber is half filled due to an assembly with a pre-bent actuator diaphragm. When a negative voltage is applied to the pump, the chamber expands and the inlet valve is opened to fill the chamber. Finally, to empty the pump chamber, a positive voltage in the range of 80 to 300 volts is applied to the actuator. As the micropump can be operated at a frequency of 40 Hz, but the highest investigated symbol frequency is 3.5 Hz, multiple pump strokes are observed at the receiver as a single injection with a larger volume. 6 different amplitude levels were implemented, ranging from 0 to 28 microliters. For each level, the injection volume was increased by half a pump stroke. In the graph, you can see the normalized resonance shift measured at the receiver for individual bursts with different amplitude levels. The resonance shift has a linear relation to the injected volume of nanoparticles. The receiver is based on the LDC 1612 evaluation module from Texas Instruments. It is fitted with custom-made coils through which the transmission channel is passed, causing a change in inductance as the spions flow through the channel. The sensor then records the change in resonance frequency. We now use these hardware components to achieve data transmission by encoding a binary message as amplitude modulated spion injections. Each symbol can have 6 different amplitude levels, and 2 symbols are grouped to a word, resulting in 36 possible combinations. We encode 5 bits, so 32 possible combinations, to these words of 2 symbols. The table shows the complete coding alphabet with the first symbol denoted as S0 and the second symbol as S1. The most common error syndrome at the receiver is a symbol wrongly decoded with an offset of 1 value. We therefore applied the concept of 2-dimensional gray coding with only a single bit change for neighboring words. As a result, only a single bit error occurs for the typical syndrome. One of the neighboring binary sequences was chosen arbitrarily for decoding the unused words marked in blue in case of a transmission error. Each transmission is initiated and terminated with a symbol of the highest value to simplify symbol synchronization. Words are decoded at the receiver using a MATLAB script and machine learning. First, however, a moving averaging filter with a length of 2 symbols is applied to the raw sensor data to reduce noise. Next, the data points are increased to a sample rate of 100 samples per second using cubic spline interpolation, and both the signal's 0 baseline and the initial synchronization peak are determined. Then, the symbol intervals with a known duration are applied, resynchronizing on high symbol values to allow for timing inaccuracies. For each symbol interval, 3 different signal parameters, chosen by a feature extraction algorithm, are recorded. Finally, these parameters are passed to a fitted discriminant analysis classifier for symbol prediction. A different detection model was trained for each symbol rate. Here you can see a sample transmission sequence consisting of 8 symbols. The 3 detection parameters, rising edge height in green, amplitude level in purple, and falling edge height in red, are indicated for 2 of the symbols. The amplitude levels are set at the highest local maximum with a sufficient prominence within the symbol interval. The minimal values within one symbol interval before and after the symbol's maximum are used to calculate the heights of the rising and falling edge. These values are then normalized to the initial synchronization peak. The rising edge height is the most dominant predictor variable for the transmitted symbol value. Looking at the distribution of the parameters over the symbol range, rising edge height in the top left corner, falling edge height below, and peak amplitude on the right hand side, you can see that a simple threshold detection is not possible. Although the mean values show a consistent pattern, the large spread of the parameter values causes large overlapping areas. By combining the information of all 3 parameters in a classification model, the decoding accuracy was significantly increased. We evaluated the data transmission capabilities for 4 different symbol rates ranging from 2 to 3.5 Hz. For each symbol rate, a random sequence of 2000 bits was transmitted, decoded, and inspected for bit errors. In the decoding sample on the right-hand side, you can see a typical symbol error. For the second symbol, a value of 2 was transmitted, but falsely decoded as 1. Due to the choice of grey code, only a single bit error occurred in the binary transmission, leading to a significantly lower bit error rate than symbol error rate. The overall error probabilities for all 4 symbol rates are shown here. The average error probability is 24% for symbol errors and 10.3% for bit errors. We cannot observe a significant correlation between error rates and the symbol interval length, indicating that even shorter symbol intervals may be possible with comparable results. An analysis of symbol errors confirms our coding hypothesis. In nearly all cases, the difference between the transmitted and detected symbol is no more than 1 value. The results are similar for all investigated symbol intervals. We now want to calculate what data rate is achievable using the presented transmission method and compare the scheme using amplitude modulation to previous results. Our whole transmission from encoding the binary message to decoding the transmitted 2 symbol words can be regarded as a binary symmetric channel with a channel capacity C of 1 minus the binary entropy function H2. Together with the noise channel theorem and the error probability F, we can calculate an upper boundary for the possible data rate in the transmission system for a given remaining bit error rate BER. As a comparison, we use data from a previous publication for molecular communication using on-off keying under the same testbed conditions. In direct comparison, we can see a significant increase of achievable data rate for a symbol interval of 0.4 seconds. The best data rate achieved for on-off keying with a bit error rate of 1% was 2.3 bits per second. Under the same conditions, we nearly doubled that value with 4.5 bits per second by using amplitude modulation and the presented coding scheme. In conclusion, for the first time, amplitude modulation was successfully applied to a molecular communication testbed with spions using a micropump. This allows for a nearly doubled data rate and significant step towards miniaturization in comparison to the previous setup. The overall bit error probability was 10.3%, with no correlation to the symbol interval. A further increase of data rate by increasing symbol frequency could be possible. In future, we will increase the receiver sample rate to accommodate for shorter symbol intervals. The sensor coils could also be optimized to increase sensitivity. Finally, a significantly larger training set for the machine learning-based detector might yield improved results. I would like to thank the German Federal Ministry for Education and Research for supporting the project for macroscopic molecular communication and making this research possible. Thank you very much for your attention.
Hi everyone, my name is Maria Imdad and I am here to present an enhanced DNA sequence table for improved security and reduced computational complexity of DNA cryptography. The outline for this presentation is a brief introduction of DNA, work done so far, proposed table and its strength, entropy calculation for base and proposed table, step-by-step explanation of the algorithm, experimental results to compare both tables, and concluding remarks. Introduction. Body of all the living organisms is made up of DNA, deoxyribonucleic acid. Each cell has a nucleus and this DNA is inside the nucleus. It is unique for every individual. That is why it is used for identification in most of the cases. DNA is being used in polymerase chain reaction, DNA sequencing, DNA synthesis, and digital coding. DNA can store a huge amount of data. For example, a single gram of DNA has 1021 nitrogenous bases. Nitrogenous bases, these are adenine, guanine, cytosine, and thymine. And these bases can hold approximately up to 108 terabytes of data. And DNA for digital coding uses DNA bases, that is adenine, thymine, guanine, and cytosine. These are the bases which are binary coded as 00, 11, 10, and 01 respectively. And this is the digital coding which will be used throughout this research. Related work. This is an insight where DNA coding has been used in cryptography. Along with this, there are other techniques where DNA has been used, but it is not for digital coding, but there are other purposes for DNA sequencing. So here we can see that the base table has been created for 96 printable characters, and all of the other techniques are using this base table along with any other modification. For example, some of them may be using it in a combination with image encryption, with socket programming, but the same base table is used in all of these techniques. Related work. This is the base DNA table proposed by Nurulhussain. This is the table generated randomly after every iteration. So the encoding value will differ in each of the iteration. For example, in first iteration, A may be depicted as ACAT, but in the next iteration, A may be depicted as CTCG. So the values of the alphabets will change in each iteration. But there is no frequency count or entropy consideration for this base table. There is no randomness criteria that can be used to introduce more randomness into your ciphertext. Proposed table. This is our proposed table. It contains exactly those 96 characters as we have in the base table, and these are 96 ASCII printable characters, and all of these has been encoded here. But the difference between the proposed and the base table is frequency count, randomness, entropy, and probability consideration. We'll go through each of them one by one. Frequency count of each character has been kept in consideration. As we can see that in table we have a column called rank. The rank column sorts each character on the basis of frequency, so that the characters having the highest frequency will be ranked as 1, whereas the character with the least frequency, with the lowest frequency, will be ranked as 96. Here we can see that E is ranked 1 because it has the highest frequency occurrence, whereas for the euro sign it has the least frequency occurrence, that is GTAA. It is encoded as this. Next is randomness. Randomness is where the higher frequency characters will have the most random codes while leading to repeated codes for the low frequency. Here we can see in the table for E, our generated code is ATCG. It has all of the 4 nitrogenous bases: adenine, thymine, cytosine and guanine. But in case of uracil, we can see that GT is different, but A is being repeated twice. So the highest frequency characters will have codes with non-repeating nitrogenous bases, but for the characters where our frequency is very less, the repeated codons can be used. This leads to the foundation of probability for coding. Here we have kept the probability of each base is 96, and whereas the combined probability of all the bases is 384, and this probability will yield to the higher entropy, as we can see in the subsequent slides. Entropy calculation for DNA table. Here we have calculated these 2 equations give an insight of the entropy for both of the tables. Higher the probability, less is the uncertainty, and more is the information being retrieved from the ciphertext. For proposed table, entropy of each DNA base is same, yielding a balanced value of 2. Whereas for base table, the probability of A is equal to 83, C is equal to 106, G is equal to 96, and T is equal to 99. And the entropy here in this case is 1.9164. The difference may not be very significant right now, but we can get an insight that it has a huge impact on the output. Algorithm. This is the algorithm that has been tested for proposed and base technique. And here we can see that the green highlighted point is where previously we had the base table, and now we have introduced the proposed table. The algorithm will run for both base technique and proposed technique, given same plain text and same key, and we will check out the ciphertext, and the difference in the values of the ciphertext will be identified. We will quickly go through the steps, starting getting the plain text from the user, passing it through the base or proposed DNA sequence table, converting it into a 2-bit binary string. Once the binary string is achieved, it will be XORed with the key. Then it will be converted again into a DNA sequence table, a DNA sequence like 00 will be converted into A, 01 will be converted into C, something like this, and then converted sequence will be converted into messenger RNA using a messenger RNA table. That is another dedicated table in the algorithm which will be used to convert our sequence into messenger RNA. First we have got the messenger RNA, now we will convert it into transfer RNA. This is the process where messenger RNA string will be replaced to transfer RNA string using the base, interchanging the base of thiamine to uracil. This is the exact simulation of DNA replication procedure, and dividing this, next step is to divide the transfer RNA and to create a new transfer RNA. Here what we do is that we divide the transfer RNA string into 2, and the second half will become the first half and the first part will become the second part. And then after this we apply the reverse simulation, that is we will reconvert uracil to thymine. Last is the usage of amino acid table on this string to convert it into ciphertext, and then we will stop the algorithm. Experimental results. Frequency analysis of the encoded text. Values has been calculated at a point where plain text has just passed from the DNA sequence table. Output from this step becomes 4 times the input, which means that in case of 3000 characters and as input, we have got 12,000 characters of DNA bases as output. Ideally, for a balanced output, each base value should be equal to 3000. In case of base technique, it ranges from 1938 to 4830 for each base, but for the base technique, it ranges from 2933 to 3036, which doesn't deviate much from the ideal value. Similar is the case for input of 6000 characters. Computational time for encoding process. This is the time calculation for the second step of our algorithm. For encoding only, the time difference has been calculated, where it is evident that this difference is nominal in case of small plain text size, but as the input size increases, the difference becomes visible. Here we can see that if we have small input of characters like 50, 150, the difference is very small. The difference is not visible at all, but as we move to large input of characters like 2500 characters, we can see that the proposed technique is taking much less time as compared to the base technique. Frequency analysis of ciphertext. Once the ciphertext has been generated from the plain text, it is received as English alphabets, as we know from the amino acid table, that ranges from A to Z. It can be seen from the figure 5 that the highest frequency in case of proposed technique is 37 for V, and for the base technique it is 66, which is for P. Here even the highest frequency of our proposed technique is far less than the base technique, yielding a more balanced output as ciphertext. We have encryption time comparison for base and proposed technique. Figure 7 gives a comparison of the time for both techniques against the input size. In all cases, proposed technique is taking very less time as compared to the base technique. This is because of the ranking in the table and the encryption design, like E is highly occurring, so it will be encoded first. That is the schema behind this, and that is why in all of these cases we can see that our technique is taking much less time as compared to the base technique. Entropy analysis. Figure 8 has entropy for ciphertext. Ideally, the entropy in the given scenario should be 4.7, which is 26 characters are being used to represent our ciphertext. So the ideal entropy for this scenario should be 4.7. But as we can see, the entropy for ciphertext for base technique ranges from 3.9 to 4.16, while for the proposed technique it is from 4.24 to 4.35. We can see that even the proposed technique has not yielded an ideal entropy. Still, the entropy yielded by the proposed technique is better than that of the base technique. Even the least entropy achieved by proposed technique is better than that of the base technique. Base technique's best entropy. Conditional entropy. It is the information about the plain text given the ciphertext and the key. Like our attacker has the ciphertext and the key, but we want to calculate how much information he can get. Higher the information leakage, it is like bad for the algorithm. Lower the information leakage, it is good for the algorithm. Here we can see that in case of base table, it is 1.5969, while for the case of proposed table, it is 1.12, which is significantly very less than that of the base technique. Conclusion. Traditional cryptographic techniques cannot be used as a standalone solution for modern era. It can be combined with DNA cryptography and then it can be used. DNA cryptography has other forms as well, like DNA polymerase chain reaction, DNA digital coding, DNA synthesis, but DNA coding is the area where most of the work is being done. And this paper has improved a base table And for the performance evaluation, implementation of the both table indicate that the proposed table gives a balanced frequency in encoded and ciphertext, reduced encoding and encryption time, achieved better entropy for the ciphertext. Conditional entropy is less in case of base technique, that the information leakage being produced by the by the proposed technique is less than that of the base technique. The entropy of the proposed table is slightly less than that of the base table, but it has a huge impact in terms of randomness and time. So we can safely say that this table can be used as a substitution for the base table to reduce time and increase the randomness in ciphertext. Finally, we are very thankful to all the reviewers for their helpful comments, Ministry of Higher Education Malaysia and UTHM for funding this research. Thank you.
Hello, my name is Florian Lau, and today I'm going to hold a presentation on the basics of DNA-based nanonetworks, or how to perform general computations at the nanoscale. But first, I want to present a small intuition for the nanoscale. As we can see here in this chart, there are different items ranging from a tennis ball, the size of 10 to the power of 8 nanometers, down to glucose molecules, which are less than 1 nanometer in size. The interesting interval, however, lies between 1 and 100 nanometers, and in this interval there are structures like proteins, DNA, viruses, but also other things like liposomes and quantum dots that are also used actively at the nanoscale. For the sake of this presentation, however, proteins, and to be more specific, DNA, are of special interest. But without further ado, let's get into a small motivation why I think DNA-based nanonetworks are of interest to medical applications, for example. For this, let's imagine a patient that suffers from multiple diseases. In reality, right now, this person has to stay at hospital stationary most of the time, so the person's health parameters can be tracked. The alternative to this is that a doctor injects a swarm of nanorobots or a whole nanonetwork into this patient's bloodstream. The nanorobots then measure the health parameters of this person and transmit the information to a remote doctor. And the doctor can then make judgment calls for the health parameters and maybe even instruct the nanonetwork to release medication, as an example, and the quality of life of the patient is greatly increased. But what do those nanonetworks or nanorobots consist of? Well, there are certain different building blocks that can be used to create nanorobots. First, we can use bacteria by modifying them so they fulfill the function of nanobots in general. Another approach would be to further downscale already available robotics technologies to make them nanoscale in size and use them at the nanoscale, for example, for medical purposes. And the last bit of technology is DNA-based nanorobots. In this case, we can use simple building blocks that self-assemble into more complex structures that can fulfill the role of nanobots and even nanonetworks. And in my opinion, the DNA-based approach is the most promising approach right now, as DNA is quite versatile and an already available material that we can mass produce in many laboratories around the world. Okay, but let's now have a closer look at this nanonetwork here. What does it consist of? As we can see here, we have a swarm of nano devices, and these nano devices are pre-programmed to be able to detect a certain environmental parameter or a marker, for example, for a disease. Once such a marker is detected by a nano device, these nano devices release building blocks for messages. And these messages self-assemble until they are complete. Once they finish their self-assembly process, they circulate in the bloodstream of the patient or in any other communication medium and can attach to other nano devices that can then react to the detection of the message. They can then in turn release certain markers that indicate a detection of a disease, for example, or directly react by releasing medication. Okay, but now what are the building blocks, or what are possible building blocks of such messages? One possible building block are DNA tiles. We can see one of those DNA tiles in this picture here. As we can see here, the structure does not resemble the classical double helix structure of the human or, in fact, any living being's DNA. And the classical binding rules of DNA are still intact, and the base pairs adenine and thymine can form a binding, and the base pairs cytosine and guanine can form a binding. What is different about this structure is that we have 4 strands and not 2 that form a square structure. 4 strands are intertwined in a way that there are 4 open ends of DNA with some base pairings in each direction. And other DNA tiles can now interact with this tile, for example, when they have a matching base sequence. And thus, those tiles can assemble into very complex structures in a programmed manner. So, but what can we now construct out of these tiles and other, well, procedures at the nanoscale? As we can see here, we have tons of nanostructures that were already possible to create in 2015. In the top row, we, for example, see the DNA tile I already presented and lots of different variations from it. In the C row, we have DNA sheets and stars and smiley faces even that have already been created in 2006. Below that, there is an open and closable DNA box that we will have a look at later. And there are also lots of other three-dimensional structures that can already be created. But let's now have a formal definition for DNA tiles so we can understand the remainder of the presentation. Tiles, when we model them mathematically, are non-rotatable blocks, as we can see to the right. Those blocks have glues on each side, and those glues can have different strengths. The number of black boxes represents the glue strength. To the left we have a glue of strength 2. To the top and to the bottom, for example, we have a glue of strength 1. Each glue has a label, and only glues of matching labels can interact with other glues. With DNA, those glues are obviously implemented by open base pairings. Mathematically, a label suffices. In the middle of the tile there is a marker, and this marker can be used to indicate the result of a computation or, for example, a truth value. When we observe self-assembly processes at the nanoscale, that is obviously not easy, and we have to use some kind of radioactive or fluorescence marker to detect the result of a computation if we want to know how the structure is assembled, as we cannot look in much more detail without influencing the result. But those tiles have even more interesting properties. For example, tiles can be used to compute. In fact, they are Turing complete, and we can therefore compute everything a regular computer can do with DNA tiles. Further, as we have already seen, tiles can be used to construct structures at the nanoscale. And tiles can also be used to communicate in networks just via binding reactions. And one additional property is also interesting. Tiles are influenced by the environmental temperature that we mathematically model by just an integer value. And let's now have an example. As we can see here, the process of self-assembly of tiles usually starts with a tile sigma. This is a temperature 2 system, which means that at least glues of strength 2 have to be involved to form a stable binding with the assembly of tiles. In this case, only the bottom glue A can interact with other tiles, and one possible match would be the tile capital B. This in turn has an open glue to the left, labeled B, and another tile can interact with it. One possible fit would be this tile 1. Now we have a more interesting situation, as the glues that constitute a stable binding can also be provided by two different tiles. When there is another tile that has a glue with label 0 and strength 1 to the right, and a glue with label 1 and strength 1 at the bottom, it can attach here as this tile 1. And since we can have inputs from two different tiles, we can encode conditions in the assembly process and thereby compute. When we want to look at the whole process in DNA, it would look something like this. We have a stable assembly of 3 tiles plus random stuff at the outside, and another tile in the process of binding with matching base pairings. We can see here that the base sequences are complementary, and therefore a binding can take place. But let's now take the two-dimensional building blocks and augment them to the third dimension, since three-dimensional building blocks are of interest to many applications. As we can see here, we can just take this tile and add possible glues to the front and to the back of the tile. With DNA strands, it would look something like this. It resembles a three-dimensional Cartesian coordinate system. And these three-dimensional structures can, for example, be used to create boxes or other structures out of DNA using tile-based approaches. But let's now have a look at the box that I previously presented in the summarization graphic. As we can see here, we have a box that is created from a different procedure named DNA origami. In this procedure, a long DNA strand is folded with itself to form sheets of DNA that in turn are folded with other sheets of DNA to form this stable box. This box has a lid, and this lid binds with the remainder of the box. And these boxes here are the basic building block for the conditioned release of, for example, medication and tiles as presented in the first scenario I showed you. And this is the same structure under the atomic force microscope. The mechanism of the DNA box is actually quite simple. The lid of the box is bound to the remainder of the box with a relatively weak binding. Once a specific matching DNA marker sequence is present, it can bind with the lid and thereby break open the binding with the remainder of the box, and thereby the payload, whatever is inside the box, is released. This payload could be tiles or medication or some fluorescence marker as already presented. But let's now come to an interim conclusion. What are the results so far? Until now, we mainly constructed using DNA tiles. But how do we compute and communicate? Well, a computation can take place inside of a message instead of the nanorobot, and the restrictions inside the communication channel where this assembly process takes place are much less severe. And the computations are conducted via a conditional assembly process. The inputs for the computations are supplied by event-based releases of specific tiles. And only upon the successful formation of a ligand after a successful computation, the message can be fully assembled and thereby detected by other devices at the nanoscale. And the obvious advantage of this approach is that there are much fewer resource constraints in the communication channel than in very tiny nano devices. But let's now have an example computation to understand the process. This here is the tile set that is necessary to perform a 4-bit AND computation, the logical 4-bit AND. And as always, the process starts with a tile sigma. At the top, at the bottom, and at the left, there can be tiles attached. The red tiles are the inputs. The top row that will just form and the bottom row are just framework structures that ensure a good assembly procedure. Now we have other tiles that can attach, and now the actual inputs can continue to attach. And this process pretty much repeats until all the inputs are attached to the message molecule. And now we have a special situation. The ligand or receptor can only form once all the 4 tiles here are present, and only then. Now the receptor can form, and this message molecule can be detected by other devices. But only when all the tiles 1 to 4 are present, and therefore the logical 4-bit AND is implemented. At the nanonetwork, the whole process would look like this. We have a swarm of nanosensors and environmental parameters that are detected by the nanosensors. Those nanosensors then release tiles, 1, 2, 3, and 4. The remaining tiles are inside the channel all the time, and the message molecule starts forming. Once the message molecule is fully formed, they circulate the bloodstream and can be detected by nanorobots, which then in turn can detect or react to the, message molecule. But that's not the only thing we can do. We can also compute more complex function problems that do not have a binary output, but a number as an output. What is displayed here is the algorithm that performs an addition of two binary numbers in tile format. The process starts again with a tile sigma, and this is a temperature 3 system. We assemble some framework structure and then attach binary numbers to the message molecule. And now only one specific tile can attach here. To the right and to the left there are carries. Right is the input carry, to the left is the output carry, and the whole procedure is in correspondence to the classical addition circuitry. So only this tile can attach here, and what's displayed in the middle is always the truth value. And we can proceed with the assembly of this message, and as we can see here, the result of the computation is the binary value, the sum of the binary values of the top row, 1, 0, 1, 0, and 0, 1, 0, 1, which is 1, 1, 1, 1. And then a ligand can form, and the assembly is finished. As a DNA-based nanonetwork, the whole thing would look like this, very much the same as the previously shown addition network, with the difference that now full binary numbers are released by the nanosensors, the rest is the same. But how can we generalize this procedure to compute pretty much everything we want to compute? And the general procedure is quite simple. First, we transform a computational problem into a Boolean formula, if possible. Then, we create a truth table for this Boolean formula. Then, we compute the disjunct normal form of this truth table and create a message molecule for each clause that has a 1 in the final row. And the Boolean formula is successfully evaluated once a single message molecule forms. But let's now have a closer look at the procedure. Here is the general truth table. We take one row with a 1 at the end and create a message molecule that functions pretty much the same as the AND that I already presented. And this is what is created for each row. We take the truth value and create a tile type for it, no matter if 1 or 0. And then the remaining structure is pretty much the same as with the 4-bit AND. And this whole message molecule can only form if each tile that is necessary is present and has the correct truth value. And as soon as one of those message molecules is created, or fully assembled, the computation is finished. And as a network, the whole thing would look like this. The nanosensors release the conditional tiles that have been presented in each row. So each tile type here, corresponds to the truth value of a literal. And as soon as all the necessary tile types for one of those message molecules are present, they can fully assemble and then be detected by nanorobots, and we thereby can perform arbitrary computations at the nanoscale. And this here is a list of solvable problems at the nanoscale that are in the complexity classes that are described by Boolean formula. And as we can see here, there are quite a lot of problems that can even be combined into way more complex computations. And the advantage of this procedure is that it has much less overhead than simulating Turing machines via tile assembly systems. It creates fewer errors since the structures are smaller, and the binding processes are much more realistic at the nanobots because the size restriction of the message molecules is in place. They cannot grow indefinitely, while Turing simulations are rather big. And let's now come to the summary. What have we achieved with this paper? First, we suggested DNA is a suitable material for construction, computation, and communication, and that it can even be used to perform arbitrary computations that can be expressed as a Boolean formula. It is possible to create fully functional nanonetworks just from DNA as a building block, and it is therefore also possible to compute any Boolean formula. And anything that can be computed by a Boolean formula is, well, quite a lot of different computations. And in summary, DNA-based nanonetworks only rely on already available technologies and can be used to perform complex and arbitrary computations, which is quite a major goal, since right now we can do practically nothing at the nanoscale with already available technologies. Okay, that's pretty much it. Thank you for your attention. Let's now have a small look at the bibliography. Now there is time for questions.
Hello, thank you all for being here. I am Mohsen and today I'm going to talk about neural communication. I'd like to begin by telling you more about the title, A Model for Electro-Chemical Neural Communication, which is a joint work by Dr. Hamid Farhadi from KTH University in Sweden, Dr. Reza Qazizadeh and me from Birjan University in Iran. This work is based on my research in visiting duration at KTH under the supervision of Dr. Hamid Farhadi Research Group. Neural communication, so-called neuro-spike communication, is a complex and heterogeneous intra-body communication system and consists of unreliable components like neurons and synapses. The system that controls all our body activities such as moving, thinking, sensing, and emotions is a complex communication process. Therefore, it has been a challenging task to model the biological neural networks. Here, we investigate the performance of a neuro-spike communication link consisting of two successive neurons and multiple synapses between them. The main motivation for investigating such systems is enabling the quantitative evaluation of communication quality in biological neural networks. Also, we hope this work helps to develop a systematic method for the assessment of the effectiveness of medicines on brain performance. So, we first refer to the physiology of the central nervous system. We discuss the transmission of neural signals within neurons and the synaptic channels. We also mention several disruption cases in the transmission of neural signals. After that, we model a neuro-spike communication link. Next, the detection error probability for the model is evaluated, and the simulation results are presented. Then we express the impact of model parameters on some specific nervous system diseases, and at the end, conclusion and future works are depicted. Let me begin with explaining more about the human nervous system physiology. The central nervous system, containing the brain and spinal cord, controls and transfers vital signals through the body and contains more than 100 billion neurons. A neuron contains three main parts: dendrite, cell body, and axon. You can see in the right a typical neuron that starts from the brain and goes to the spinal cord. Incoming signals enter this neuron by the dendrites. Then, in the cell body, all incoming signals are aggregated and the output signal travels by way of a single axon covered by a myelin sheath and leaves the neuron. The axon has many separated branches to other parts of the nervous system. But how neural information enters the neuron and travels from a neuron to the next? Let me explain in the following slides. Information is transmitted in the central nervous system mainly in the form of nerve action potentials called sometimes spike trains through a succession of neurons one after another. First, in a resting manner that there is not an excitation, the neuron is polarized. An intracellular membrane potential is about minus 75 millivolts. That means inside neuron potential is 75 millivolts less than the outside layer of the neuron. When a signal is received in the neuron due to ion exchange, such as potassium, sodium, or chloride, potential increases in the positive direction. This positive increase in voltage above the normal resting potential is called the excitatory postsynaptic potential, or EPSP. If this potential rises to a high value more than firing threshold, which is about minus 45 millivolts, an action potential with a magnitude of about 90 millivolts at a time period of 1 millisecond will be generated, which is equivalent to a delta function. An action potential should be passed through the axon and reach to the terminals. Now it causes the release of some neurotransmitters into the cleft between neurons that is named synapse. But what happens at the synapse that causes the neural signal to be transmitted to another neuron? The synapse is a narrow cleft between two successive neurons, respectively are called presynaptic neuron and postsynaptic neuron. As we said, when a spike reaches to the axon terminals in the presynaptic neuron, a chemical substance, often called a neurotransmitter, will be secreted into the synapse. And this neurotransmitter, in turn, acts on receptor proteins in the membrane of the postsynaptic neuron to open the cation channels that conduct sodium ions into the next neuron. Thus, the influx of positive ions into the nucleus of the next neuron excites it, increases its voltage to the threshold, and generates a spike. Opening other channels make inhibitory or modify the neuron sensitivity in some other ways. However, the nervous signal may be blocked in its transmission from one neuron to the next, or maybe a false signal is generated while there are not any signals. All these connections can be classified as synaptic or axonal communication disruption. I'd like to introduce several disruption cases, such as multiple sclerosis, MS, which is an axonal disease. In the central nervous system of patients with MS, axons are demyelinated, and thus the neural spike is blocked while passing through the axon. Also, Alzheimer's disease is associated with synapses loss due to the accumulation of amyloid beta in the synapse. In the case of using drugs such as cocaine, the substance of cocaine blocks the channels on the neuron's terminals and prevents the entry and exit of neurotransmitters. Alcohol alters neural connection by an undesirable increase in absorption of chloride ions, results in lowering of membrane potential and making the worst situation for excitation. Well, the neurosphere communication is subject to multiple random sources of disruption, such as axonal noise, random neurotransmitter release, random temporal and spatial aggregation of neurotransmitters in the cell body of postsynaptic neuron, and stochastic synaptic operation. Now, regarding to the given description, we could start to model a neurosphere communication link that is complex and heterogeneous communication process. First, to model the presynaptic neuron as a transmitter, we consider a neural signal as a spike train shown by xt, which should travel through the axon and causes neurotransmitter release into the synapse. The axon operates similar an AWGN channel with the power spectral density of SNF, and thus we can write signal to noise ratio as SNR axon. Release process of neurotransmitters in axon terminals could be modeled as a binary Z channel with a stochastic parameter PRR. Sure, when there is no neural signal, no release happened. And when there is a neural signal with a probability of PRR, the neurotransmitters are released, and with an error probability, the neurotransmitters are not released. To model synaptic channel, we should mention that there are different types of neurotransmitter in the synapse. Some of them make open cation channels on the postsynaptic neuron and entering of positive ions, which as a result the neuron will be excited. Inversely, some neurotransmitters open anion channels, Then negative ions enter to neuron and inhibit it. This process is modeled as a binary X-channel with stochastic parameters PRC0 and PRC1. Finally, to model postsynaptic neuron as a receiver, we should introduce two concepts of spatial summation and temporal summation. The excitation or inhibition impacts of all synapses are aggregated in the interior of the postsynaptic cell. This process is called spatial summation, and it is modeled as a binary Z-channel with a stochastic parameter PRS. Also, the postsynaptic response to the successive neurotransmitter release into a single synapse, thus after firing, is called temporal summation, and it can be modeled by QHT, where HT is an EPSP waveform of a fast voltage-independent AMPA-like synapse, and is modeled as an alpha function, and Q is a random variable amplitude which is modeled by a gamma distribution. The graphical representation of the mathematical model for a neural communication link is shown here. Suppose a neural signal is generated in the central nervous system and should travel through the investigated neural communication link. Now, I'd like to compute the error probability of signal detection in the receiver neuron. First, we define the likelihood ratio as is shown, with a decision threshold of L0. Then we rewrite it as LSY with a new threshold which is obtained as a function of L0 and the model random parameters. Now, via a detection criteria, we decide which hypothesis regarding to presence or absence of input neural signal is true. Finally, we compute the detection error probability as a function of model stochastic parameters. In the following simulation, results are depicted. Here, the detection error probability versus axon SNR is shown. It illustrates that with an increase in the SNR, the error probability decreases. The bit error rate versus neurotransmitters release probability for different synaptic error probabilities is shown in this picture. It is obvious that with an increase in the PRR, the detection error probability decreases. Also, increasing of synaptic channel error probability increases the detection error probability. In the worst case, with the most synaptic channel error, the red curve, it is shown that even the increase of release probability cannot improve the detection process. The bit error rate versus probability of a spatial summation in the postsynaptic neuron is depicted here. The increase of a spatial summation probability deals to more cooperation among the synapses for exciting the neuron, and as a result, the detection error probability decreases. Now, I'd like to discuss about impacts of the model stochastic parameters on the nervous system diseases. As we mentioned in slide 6, a certain axonal diseases such as MS is due to the demyelination of axon. Therefore, in such case, the value of axonal SNR is low, and as shown in the simulation results, the signal detection at the receiver neuron with a high probability is failed. Also, in the synaptic channel diseases such as Parkinson, schizophrenia, and Alzheimer, due to the synapses loss, the error probabilities of synaptic channel are high, and thus neural signals will be blocked while passing through synapses. In this work, first, a model is developed for neural communication based on the physiology of the human nervous system. Next, neural signal detection is evaluated by quantifying error probability in certain scenarios using this model. And then the impact of different sources of disturbance on the brain has been investigated using the developed method. We are going to develop a systematic method for the assessment of the impact of specific nervous medicines and treatments on nervous by communication using this model in our future work. Thank you for your attention. If you have any questions or you are interested in this topic, please contact us via the email addresses in the first slide.
Hello everyone, my name is Ziquan Yu and I am delighted to present Activity Monitoring using Smart Glasses, exploring the feasibility of pedometry on head-mounted displays. In recent years, step detection and counting, also known as pedometry, has gained so much attention as several commercial and health assistive applications rely on accurately detecting the number of steps that a person takes. There are many applications for pedometry. One of them is fitness tracking, for which we intend to keep track of the number of steps, the caloric intake, the distance, and also the speed of walking. Another application is in gaming, for which the navigation and the live location of the person is being tracked. Also, indoor navigation, which can have an assistive role for the visually impaired, is another area of application for pedometry, and it's yet to come and remain one of the grand challenges in mobile computing. A pedometer can be an excellent exercise device because you can track the amount of exercise you get each day. It can also be a motivational tool for a person because it allows them to set daily goals for steps. Health professionals recommend a person to take 10,000 steps per day. For those who cannot reach 10,000 steps in a day, you can use a basic method to set a pedometer goal, which is to track the amount of steps you take in a week and try to increase that by 10% each week until you reach 10,000 steps daily. There are several devices that are used for pedometry. They are typically handheld, wrist-worn, or ankle-worn wearable devices that can provide high accuracy for step detection, and they are widely available in the market. These devices usually have an accelerometer and they run some sort of peak detection algorithm on the acceleration signal to report the number of steps, and they usually do well in terms of accuracy. One of the well-known and mostly used peak detection algorithm is called the windowed peak detection, or simply WPD. This algorithm uses a moving average to smooth the accelerometer signal, and it detects single peaks via a fixed-sized sliding window. It finds the maximum value in the window, then it shifts the window, and then it discards the chosen maximum if it persists for 2 windows in a row. This algorithm has been identified as an optimal step detection approach for wearable devices owing to its computationally inexpensive nature. Smart glasses and generally head-mounted devices are vulnerable to external sources of error, such as head movement, and because of their small sizes and issues related to heat and battery, they require low computing power. To show the significance of our results, we compare the accuracy of our approach to a well-known windowed peak detection algorithm. In the study, we provide a salience-based algorithm that can provide that can be applied to the accelerometer data from a smart glass to robustly detect steps. Podometry should not be limited to smartphones and activity tracking devices. In the last few years, interest in smart glasses has been substantially growing, as has the number of influential companies such as Amazon, Microsoft, Facebook, and Apple that are announcing their entry into the smart glasses market. It is expected that the combined market size for smart glasses will grow at an exponential rate of 76% annually, and it will reach $16 billion by 2025 globally. However, smart glasses and in general head-worn devices are typically vulnerable and exposed to external sources of error. The head is the furthest body location from the ground, and naturally it absorbs less amount of shock as the foot strikes the ground. That's why the acceleration signal recorded from the head becomes significantly dampened, which makes the calculation of steps from the head location signals a challenging task. To motivate the problem, we conducted an experiment where we attached 6 inertia measurement units, or simply IMUs, produced by Schirmer Research to different regions on the subject body and asked him to take 220 steps. We used the windowed peak detection technique to derive a number of steps for each IMU. From this table, we observed that the lower parts of the body, and especially the shin, thigh, and the waist area performed well, and the error from the head-mounted IMU was the highest among all the locations. In this study, we propose a salience-based approach by which we can detect and count the number of steps for an acceleration signal that has been recorded from a smart glass with a very high accuracy. We also calculate the step count with a windowed peak detection algorithm as an optimal step detection method, and show that our results show a substantial improvement in accuracy, especially for the signals from the head. Our method is composed of 6 steps. We first need to pre-process the data, find the combined acceleration signal, and calculate the salience based on that. The salience vector is the length of the longest interval over which the sample is a maximum. The key property of the salience values algorithm is that the starting point of each step has a large salience value. Hence, steps can be found by locating these prominent points. Then we normalize the acceleration signal using the salience vector and apply a threshold to the output signal to find the peaks. Since the acceleration signal is given in 3 dimensions, we first need to combine them into a single magnitude using the Euclidean distance method. That's how we calculate the combined acceleration signal. Then we calculate the salience vector. Next step is to enhance the acceleration signal by normalizing it based on the salience vector, using this formula to calculate U. Refer to the formula here. U is equal to R times S divided by max S, which makes the peaks more pronounced and diminishes the rest of the signal as shown here in the figure C. Afterwards, we extract all the elements of U that exceed a certain threshold. Here we choose the threshold to be 2/3 of max U. Then the difference vector, D, between adjacent extracted indices is calculated. We normalize D around its mean and eliminate one of the 2 points that fall within this range. This elimination phase helps to increase the accuracy of our stride detection algorithm by counting 2 closed peaks only once. The number of points left after elimination phase is indicative of the number of steps taken. So, to test our approach, we designed 2 experiments for which we recruited 10 students as subjects and asked them to take 100 steps at their usual pace for 10 times per individual on campus. For the first experiment, we utilized the USIC M100, which is a popular Android-based smart glasses device. The device's accelerometer's sampling frequency was set to 100 Hz, and throughout the experiment, the device was running an activity monitoring application based on our salience-based algorithm to detect the steps in real time. In the second experiment, we employed a Shimmer 3 IMU unit to collect the acceleration signal from the head, foot, and pocket locations. We placed the IMUs in special pocket and clipped the pocket onto these on-body locations. The steps detection was performed offline on a desktop computer. The bottom figure shows the shimmer worn by the same subject on the head. Again, the sampling frequency of the accelerometer was 100 Hz, just like the first experiment. We performed windowed peak detection for the same data in both of our experiments as a reference. Here, in the left figure, where it is the graph of the improvement in step detection error from the windowed peak detection method to our salience-based approach. The average step detection error of our approach is 2.6% with a standard deviation of 2.8, which is significantly lower than that of the WPD method, which achieved the accuracy of 21.8% with a standard deviation of 9.7. The table at the right-hand side summarizes the average error for both the WPD method and our approach. Clearly, the foot and pocket locations perform remarkably well, and both approaches achieving similar results. However, the error from the head location in our approach was significantly lower than the WPD, where our approach achieved 3.9% and WPD achieved 25.6% of average error. Overall, our approach is substantially well with the signal from the head and other body parts. So here is the demo of the activity monitoring application that runs our salience-based pedometry technique, and I'm going to play it now. Okay, so that was the demo of our application. In summary, we proposed a salience-based approach to pedometry and applied it to an acceleration signal from a smart glass for step detection and counting. The proposed approach is superior to the windowed peak detection approach that is known to be the optimal method in terms of accuracy and complexity. The average error of step detection for the head signal in our proposed approach was 2.6%, while the average error from the WPD algorithm was around 21%. We used an Android-based application for real-time computation that requires low levels of power. Our assumption in the study was that a walking activity is occurring, and based on what we calculate the steps. However, the salience-based algorithm can be modified to detect the walking activity, which is part of our future work. In our future work, we intend to extract more specific features related to pedometry from the head signal. For instance, we first want to know if the subject is moving. Movement and mobility are referred to random movements, such as shaking our feet while seated, as well as to a more periodic ones, such as walking. Moreover, in our study, we had asked the subjects to walk at their normal pace. In the future, we plan to explore the performance of the approach at different walking speeds. We already know that calculation of the steps at lower walking speeds is more challenging. In our future work, we plan to augment our salience-based approach to be able to break down each step into its constituent phase, namely the swing and stance phases as shown here in the figure. Thank you so much for watching our presentation. We will be more than happy to answer any questions, and here are our contact information. Thank you so much.
Hello everyone, this is Uğur Ayvaz, one of the authors of the paper Real-Time Human Activity Recognition Using Textile-based Sensors. I'm a research assistant and working at Istanbul Technical University Computer Engineering Department. In this presentation, I want to mention about an HAR system performed using novel textile-based capacitive sensors. Human activity recognition aims to provide information on body movements. This information can be adapted to the computer environment, and computers can turn into assistive machines that make our daily life easier. For example, computers can be used for senior care, physiotherapy, rehabilitation, gaming industry and 3D modeling, robotics, sports, personal fitness, diagnosis of disease. HAR is also used for simulating some activities in very dangerous military tasks. In the literature, there are many types of different sensing technologies for HAR. Actually, each sensor system has its own bottlenecks. Scientists commonly use sensor fusion to overcome the drawbacks. However, there is no silver bullet for HAR yet. HAR still remains a progressive field of research. In this study, we use textile-based capacitive sensors of our own production. These strain sensors are able to sense the change in capacitance depending on the elongation. One of the most promising aspects of these sensors is that they are body conformal and they are able to be worn on the entire body. The aims of this study are discovering the capabilities and limitations of the capacitive sensors in HAR, designing an HAR system using wearable capacitive sensors, performing the HAR in the real-time and real-world settings, and conducting a feasibility study for the entire body-fit version. For these purposes, we collaborate with textile engineers who manufacture the capacitive sensors. The greatest contribution and novelty of this study to the literature is the use of our own production capacitive sensors in HAR. The sensors are manufactured in the ITU labs. The sensor consists of a silicon insulator layer between two woven capacitive flexible fabrics. Each capacitive layer is connected to a microcontroller via conductive yarns. The manufactured sensors are flexible, human body conformal, and easy to attach body joints. In this study, we achieved an HAR system using capacitive strain sensors attached to the knees. The first step of the system is the activity data collection. We choose 4 different characteristic activities such as walking, running, squatting, and standing. Each activity has different signal patterns. We attach the sensors to the right and left knees of the participants and collect the capacitance variation during the leg movement. Then, we smoothened the raw signal and applied 2 different signal segmentation methods. After that, the features were extracted and the machine learning models were trained using these feature sets. In the real-time implementation, the features are extracted quickly and the machine learning model predicts the activity type. In the figure, the data transmission process is presented. The sensors are attached to the knees of the participants. Each sensor data from right knee and left knee is read and merged by a microcontroller and transmitted to the personal computer via Bluetooth. Bluetooth connection is provided by 2 Blueno modules. First one is transmitter Blueno and second one is receiver Blueno. This process works very fast and the data transferred to the personal computer instantaneously. The data transfer rate is 50 Hz. Once the signal is received, the signal processing starts. We applied the Savitsky-Golay filter to smoothen the retrieved data. To normalize the data, two different approaches are applied by taking the ratio and difference of raw sensor data retrieved from the right and left knee simultaneously. Herein, two types of signal segmentation methods are implemented. The first one is the sliding window method. We set the window size of 128 samples and the shifting size of 64 samples with the 50% overlapping. In the figure, one frame sliding window data is displayed. As seen in the figure, only one full squat was performed, as well as almost 3 right leg running steps were performed in one sliding window frame. The second signal segmentation method is onset-offset detection. In this method, we don't care about the duration of the activity. We are only considering the one complete onset-offset. This way, we obtain more balanced data. In the figure, the patterns of each activity are very similar. However, we can distinguish them by taking the difference between local minimum and peak values. We realize that more elongation makes more difference. As seen from the figure, the greatest elongation belongs to the squatting activity. Feature extraction is one of the most important parts of the HAR systems. In this section, we produced 8 statistical features from each sliding window and onset-offset detection frame for each knee. So, we have 16 statistical features for each frame. The feature names and descriptions of each feature are given in the table. We obtained 8 different sliding window based feature sets and 1 onset-offset detection based feature set. Herein, we omit the onset-offset dataset without statistical features, since each detected onset-offset frame has a different number of samples and doesn't have a regular shape. We conducted with 4 different machine learning algorithms. We trained 5 machine learning models, SVM1 and SVM2 with different hyperparameters, DT, KNN, and RF. The performance of each model is evaluated using tenfold cross-validation metric. The hyperparameters of 5 different machine learning models are given in the table. We conduct this experiment with 3 participants having the following characteristics. The sensors are attached to the knees of the participants. Each participant performed 4 different activities in different time periods. 12 minutes long data is recorded from each participant, consisting of 3 minutes for each activity. We create 2 types of datasets: dataset with statistical features and smoothened data without statistical features. In the sliding window based feature set, we also investigate different feature set combinations applying normalization techniques. You can see the squatting activity in the first 4 figures. These 2 figures belong to running activity. Each activity is collected in different time periods and recorded with activity labels. As you can see, the amount of stretching and elongation of the sensor is greater during the squat activity than during other activities. In the table, The classification results of machine learning models using sliding window-based feature sets are given. Although random forest has the greatest accuracies on 5 feature sets out of 8, it is the laziest model. It has the worst execution time. Therefore, random forest is not suitable for our real-time HAR systems. Decision tree model is the optimal model for our system in terms of both accuracy and execution time. The other statistic is that decision tree is one of the most successful models on the feature sets with statistical features. On the other hand, K-nearest neighbor has proven to be the fastest model. In fact, we achieved the highest accuracy with decision tree. We can also consider the KNN's performance, especially in the real-time systems. The classification results for onset-offset detection-based segmentation are given in the table. Herein, the highest accuracy is obtained by random forest, but the accuracies are very close to each other. When we evaluate their performance in terms of accuracy and execution time, KNN and decision tree are much better than RF. These results are the detailed classification reports of the machine learning models on the feature set 2 sensors without normalization with statistical features. Here, decision tree also has the highest F1 score. At the onset-offset detection-based segmentation site, there is one feature set, and the detailed classification report of machine learning models is given in the table. Random forest has the highest precision and F1 scores. However, it is the laziest model. The results of decision tree model are more suitable for our system design. In this slide, the confusion matrices of machine learning models on 2 different feature sets are given. As you easily realize, the data set is unbalanced. This is a natural situation for onset-offset detection-based feature set, since the activity collection duration is equal for each activity. What I mean is that, let's turn back to the slide number 11. As you see, one complete onset-offset detection times vary for each activity. One full squat lasts 2 seconds, as well as one full running step lasts 0.65 seconds. So, since the data collection time is equal for each activity, the number of samples in running activity is much greater than the others. On the other hand, the number of standing samples is much less than others, and we believe that this is one of the reasons for the low accuracy. Especially in the sliding window-based segmentation feature set, false positive and false negative numbers of standing activity affect the classification accuracy more easily due to the very small standing sample size. In this study, we applied 2 signal segmentation methods and learned the limitations of these 2 methods. Sliding window-based segmentation is suffering from transition activities, such as transition from walking to squat in real-time settings due to the fixed size frame size. Onset-offset detection-based segmentation suffers from the misdetect local minimums. To overcome this, we applied 2 different techniques. The first one is the filtering and smoothing the signal. Second, we set threshold to omit local minimums detected before the complete step occurred. In the activity classification, we trained 5 machine learning models using activity data and evaluated their performances in terms of accuracy and execution time. The overall results show that random forest has the best overall performance in terms of accuracy, but it is the laziest model, so it is not suitable for the real-time system. KNN has proven to be the fastest model. DT model performed the optimal results on both sliding window segmentation and onset-offset detection segmentation-based feature sets. We obtained the accuracy of 83% using decision tree model. We are aware of the unbalanced and small sample size dataset. Due to the COVID-19 pandemic, we conducted our research with only 3 participants and a limited dataset. We believe that collecting more activity data and using more capacitive sensors on other body joints such as elbows will improve our classification accuracy. To conclude, we carried out an HAR system using textile-based capacitive sensors that are our own production. The sensors are attached to the knees of 3 participants to sense lower limb motion such as walking, running, squatting, and standing. We compared 2 types of signal segmentation methods. We also test the performance of 5 machine learning models in real-time HAR. The overall classification results show that decision tree model is the optimal model in terms of accuracy and execution time. We achieved the highest classification accuracy of 83% with decision tree model and on a sliding window based dataset. In the future, we aim to collect more data from more participants. We also want to collect different types of daily activities and test the system's performance on closely related activities such as jogging and sprinting. We aim to use some auxiliary sensors such as IMUs beside our sensor system and apply sensor fusion. Last, our ultimate goal is to produce a one-piece sensor suite that can be worn on the entire body. This is the end of my presentation. Thank you for your attention and listening. This study is partially funded by Marie Curie individual fellowships. We also thank them for supporting us. If you have any questions, I can answer.
Hi, my name is Xiaoshen Lang, and my thesis topic is the extraction of respiratory signals and respiratory rates from the photoplethysmogram. Now, I introduce this paper from 8 parts. First of all, I'd like to welcome you to my presentation, and in the next 15 minutes, I'm going to talk about the algorithm I proposed for my paper. Here is the abstract section. Respiration rate is an important indicator of human health assessment which can be estimated by extracting respiratory signals from the photoplethysmogram (PPG). The goal of this study is to propose an alternative method for obtaining accurate estimation of respiratory rate from the PPG signal. The proposed algorithm is based on the multiple autoregressive models and autocorrelation analysis (ACAR). In ACAR, the autoregressive model is applied to determining the dominant respiratory rate from the PPG, and autocorrelation is applied to reduce the effect of clutter in the 3 respiratory induced variations. Meanwhile, this paper introduced signal quality indices (SQI) to improve reliability of the results. The algorithm is tested using an open source database, the Capno-based benchmark dataset, which comprising 42 8-minute PPG recording and respiratory signal acquired both children and adults in different clinical settings. Compared with that of existing method in the literature, the average absolute error percentage (AAEP) of the proposed algorithm is less than 3.72%, which demonstrated that our presented ACAR bring a significant improvement in accuracy. The next part is the introduction. Respiratory rate is one of the indicators used by hospitals to monitor patients for abnormal conditions, such as cardiac, respiratory arrest, systemic inflammatory response syndrome (SIRS), and renal failure. Adults have a normal respiratory rate of 8 to 20 breaths per minute. In a study of respiratory abnormalities, 54% of cardiac arrest patients had at least one 27 BPM 3 days before cardiac arrest. Therefore, it's essential to monitor patients' respiratory. However, although pulse oximetry can be used to continuously measure heart rate and peripheral oxygen saturation, continuous estimation of RR requires additional equipment, such as the measurement of gas flow. Therefore, there is a need to improve the accuracy of RR estimates from the electrocardiogram (ECG). The photoplethysmogram (PPG) obtained from pulse oximeters. This paper focuses on extracting RR from PPG signals. The modulation of PPG signals by respiratory cycle includes a variety of ways, including amplitude modulation (AM), frequency modulation (FM), and baseline window (BW). To extract the respiratory modulation signal from the PPG, the most common method is to detect the peak and throw of the PPG signal and obtain the respiratory modulation signal by calculation. Respiration leads to change in cardiac output, causing respiratory induced amplitude variation, RIAV, that is, change in peripheral pulse intensity. RIAV is defined as the height difference between two adjacent peaks and troughs. The next part is related work. Different algorithms have been proposed to estimate RR from PPG, such as digital filters, fast Fourier transforms (FFT), wavelet decomposition, and hidden semi-Markov model, autoregressive model (AR), principal component analysis (PCA), and artificial neural network (NN) have all been successfully applied to various PPG databases with good estimation results. Some studies use neural networks to analyze the three modulation signals to select the best waveform for the algorithm design. There are also studies that use data fusion to combine estimates of multiple modulation signals. However, these methods have higher requirements for time-domain waveforms. This problem can be solved by autocorrelation analysis. Autocorrelation analysis is a mathematical tool for finding repetitive patterns such as periodic signals masked by noise. Since the respiratory signal can be viewed as a noise periodic signal, the autocorrelation analysis can be used to calculate the respiratory rate. In the autocorrelation signal, each peak, except the first, represents a period of strong autocorrelation, and the period with the greatest correlation can be regarded as the RR. The next part is the proposed algorithm. As for RR estimation, the most essential is the extraction of respiratory modulation signals. The main method for extracting respiratory modulation signals are peak detection and signal quality assessment. Before the peak detection, the pre-processing procedure should be carried out fast. A high-pass filter is applied to remove the DC component of the PPG signal. Then the PPG is segmented into pulses using IMS algorithm, and artifacts are detected which are used to calculate signal quality if the assessed quality is low. The RR estimation is not provided. This paper proposes an improved method for peak detection and signal evolution, and then uses spectrum analysis and data fusion to estimate respiratory rate. In the following sections, we will describe RR estimation in more detail. The general principle of peak detection is that any singular point of a differentiable single signal corresponds to a zero crossing point or two inflection points in its derivative signal. This paper proposes a new method for peak detection. This method doesn't need to solve the second derivative, also doesn't need to solve the inflection point of the first derivative. Therefore, the computational efficiency can be improved to facilitate real-time processing. The specific method is shown in the algorithm 1 below. In order to avoid the impact of PPG signal amplitude changes on peak detection and verification, a 10-second sliding window is used for PPG waveform with an overlap time of 5 seconds. Since the upslope and downslope line segments have a 1-to-1 correspondence, the upslope line segments are analyzed separatively. If the amplitude and the slope of the upslope line segment both exceed the threshold, it is regarded as an artifact. If the slope is 0, it is regarded as a clip. The line segment immediately after the clip is also artifact. SQI is calculated according to the ratio of artifact and clip in the PPG for signal quality. If the SQI is less than the threshold, then the data window is labeled as low or estimation quality. Autocorrelation analysis is a mathematical tool for finding repetitive patterns such as periodic signals masked by noise. Since the respiratory signal can be viewed as a noisy periodic signal, the autocorrelation analysis can be used to calculate the respiratory rate. We apply the autocorrelation to analyze the signal as Figure 6 shows. As a result, the autocorrelation coefficient waveform contains the breath rate signal, and it overcomes the effect of noise and clutter. At last, we can analyze these coefficients by AR model to acquire the more accurate AR. AR model is an alternative to the discrete Fourier transform (DFT) and one of the methods of high-resolution spectral estimation of short-term sequences. In biomedical engineering, AR models are widely used for spectrum analysis of heart rate variability and electroencephalography analysis. In AR model, each point in the time series is a regression of its past points. The number m of past points used is called the order of AR model. AR model can be regarded as a filter, which divides the time series into predictable time series and prediction error series. Compared with the DFT, it provides a smoother and a more intuitive power spectrum, and yet is more completed. The next part is the materials method. The method was implemented and tested using the MATLAB software framework VR 2018A, and it was designed to be used on each single window. An open source dataset, the Capno-based benchmark dataset, was used for the analysis described in this paper. The database, which contained PPG signals, ECG signals, and respiratory signals, was collected by Cullen et al. The sample frequency was 300 Hz. This data were collected from 59 children and 35 adults. The author of the database randomly selects a part of it and then combines it into a new dataset, which contains 42 data segments with a duration of 8 minutes. Each recorded carbon dioxide 2 tracing waveform was used as a reference gold standard record for RR. Each breath on the carbon dioxide map in the database has been manually marked by the research assistant, and the reference RR value is derived based on the average time between two consecutive breaths using annotations. The next part is the result. After signal processing, we get the respiratory modulation signal from the PPG signal. Figure 10 shows the comparison between the reference respiratory signal and the respiratory modulation signal extracted using the peak detection algorithm proposed in this paper. The extracted respiratory signal is basically similar to the reference respiratory signal, which is of great help to the subsequent analysis. Following the signal processing method previously mentioned, respiratory rates are acquired through the ACIR algorithm. By the above formula and the reference respiratory rate, we can calculate the MAE and the AAREP. From Table 1, we can see that the result is much improved after using SQL in the Capno-based database. Some signals are chaotic, and the result with large errors will be obtained by using these signals to analysis. Using SQL can avoid these errors, which is beneficial to the reliability of clinical results. Meanwhile, compared with AR model, the AAEP of the ACAR algorithm decreased by about 1%. From Table 2, the accuracy is improved to some extent after data fusion with ASQ, which proves that the feasibility of data fusion using this method, compared with averaging the spectrum directly using ASQ, can dynamically select a better spectrum as a result according to the quality of autocorrelation signal. The next part is the conclusion. In this paper, we improved the method of obtaining respiratory modulation signals and proposed a new analysis method that can be used in combination with other respiratory frequency analysis methods to improve the accuracy and robustness of respiratory frequency estimation. The autocorrelation method can remove noise in a periodical signal having the above characters. Each peak of the autocorrelation sequence represents a period of strong autocorrelation, so the period of the autocorrelation corresponds to the period of the original signal. The problem is that when the waveform of the PPG signal is relatively chaotic, the respiratory modulation signal extracted from it is not reliable. If the baseline drift of the PPG signal is severe, there will be errors in the peak detection results, which will cause some peaks to be missed. To solve this problem, our next goal is to better remove motion noise, so that the respiratory rate can be extracted from people in motion. That's all. Thank you.
Hello to everyone, my name is Antoine Gauthier. I am a PhD student in the electronics team at the Institute of Electronics, Microelectronics and Nanotechnologies situated in Villeneuve-d'Ascq, France. I will present you our paper about an ultra-low power integrated heartbeat detector for wearable sensors. This work has been performed in collaboration with ST Microelectronics. This presentation will be structured in the following order. At first, we will introduce you the general context, the wireless body area networks. Then we will see the proposed heartbeat detection model. It will be followed by its description of its circuit implementation. Then we will end this presentation by the transistor level simulation and performance estimation, and end it by the conclusion. The presented work takes place in the context of biomedical sensors and wireless body area network. The practical applications of these networks are mainly at-home or clinical long-term monitoring for arrhythmia detection, as an example. These networks, depending on the application, can regroup various biosensors nodes, ECG, bioimpedance or accelerometers, at different locations on the body. These nodes communicate with a common aggregator for data collection. Communication between the sensors and the aggregator needs precise synchronization to be established. The synchronization between sensors is mandatory to establish communication and is generally achieved by three standard schemes. The first one is the use of local oscillators in the sensor nodes. This solution suffers from a high power consumption and needs a precise calibration. These characteristics are disadvantageous for long-term monitoring applications. The second solution is the implementation of wake-up receivers to let the sensors in sleep mode until the communication starts. But the wake-up receivers are always on and are very energy hungry. The last solution is to use a signal common to all the sensor nodes, the heartbeat signal, for instance. This scheme is the one studied in this work. The figure on the right shows the typical communication scheme. The heartbeat is used as a wake-up signal to initialize broadcast. The communication is established between the aggregator and the desired node. The function M by our work is the detection of the heartbeat signal and its transformation into a wake-up signal with a low power consumption. This transformation from raw ECG biosignal to the pulse wake-up signal is done in three steps. First, the electrode sensing for electrical conversion. The main critical aspect of this first stage are the number of electrodes and the adaptation on the human body. The second stage is the amplification of the electric signal. The design trade-offs of these points are made between a low power or a high precision or common mode relation ratio. And at last, we have the ECG reconstruction or threshold decision. At this point, the trade-off is made between low power versus a dynamic threshold adaptation. Secret design opportunities are located on the last two stages for low power system design. Our efforts will be focused on these blocks. Heartbeat sensing and detection is already achieved by numerous integrated circuits. We base our study on the comparison with three state-of-the-art heartbeat detectors. The system proposed by Zhang at T-Biocast 2018 is the first we studied. This circuit is an instrumentation amplifier that aims to reconstruct the entire ECG components. For this purpose, it needs a high precision and a high common mode rejection ratio and has consequently an important power budget. In addition, this system is oversight for application because we don't need to reconstruct all the ECG components but only to detect the heartbeat beat. David Hale presented a simple heartbeat detection circuit at T-Biocast 2015. This circuit used two amplifiers to amplify the differential part of the signal and the baseline. The baseline is then used as a threshold voltage for a comparator producing the output of wake-up signal. The main problem in this circuit is that the threshold voltage is controlled by an external microcontroller that limits the use in embedded wearable systems. The last circuit is the one proposed by Bose at ISSCC 2020 In this work, the threshold is no more adapted by an external microcontroller, but thanks to a dedicated always-on digital circuit. This solution is thus easier to embed, but the threshold control circuit is always on and its consumption is still high. The main axis of our work is to implement an adaptive threshold that is patient-specific, follows the ECG baseline, and is only calibrated once offline. Moreover, another key element for the wearability of ECG sensors is the electrode sensing implementation. Commonly, heartbeat detection is achieved with 3 electrodes. One of them is used as a reference to get rid of 50 Hz noise and increase command modulation ratio, and is commonly located far from the other electrodes at the left foot of the leg, for example. Because we don't need high precision and high CMR for application, we can use 2 electrode sensing only. It limits the number of electrodes on the body and improves the comfort and wearability of the overall system. I will now describe you the system level of the proposed heartbeat detector. It is composed of 4 main parts. The input stage sensing interface is used for coupling between the electrodes and the inputs of the following differential amplifiers. These 2 amplifiers share the same design. Amplifier A1 acts as a traditional differential amplifier and amplifies both the command mode and the peak of the ECG signal. Amplifier A2 is a twin of A1, but its role is only to amplify the command mode of the ECG signal. That's why it is only connected to one electrode. An additional offset is added at A2 output to further use the command mode as a reference threshold for the comparator. The amplifiers are followed by low-pass filters to reduce 50 Hz noise caused by the lack of third reference electrode. When a heartbeat occurs, the A1 output voltage crosses the A2 output reference threshold, and the comparator generates the desired pulse used as a wake-up signal. The role of the additional offset at A2 output is important. If VO is too high, the comparator will not trigger. If it's too low, it will generate too many parasitic pulses. Finally, a self-calibration unit uses the system output voltage to adjust this additional offset at A2 output. The calibration is patient-specific and is done offline at device startup. The whole chain is designed to work at a 0.9 volt voltage supply, and the main advantage of the proposed structure is to use the use of the command mode voltage as a reference signal for the comparison. Consequently, only the differential signal between the 2 electrodes can be considered, and the requirement for CMR is lowered. We'll now present you in detail the different blocks of the system. First, the sensing interface between the electrodes and the amplifier's inputs. It is implemented by femtofarad orders capacitors and large integrated pseudo-resistors in the range of the teraohm. It results in high-pass filters attenuating the baseline drift and motion artifacts. To improve the difference between the 2 ECG signals without increasing the amplifier gain and its consumption, the capacitance are voluntarily mismatched. Simulations at high-level model show that a 30% capacitive mismatch is able to produce a detectable differential voltage corresponding to the peak of the ECG signal. Amplifier structure is a conventional 3-stage amplifier structure composed of a differential input pair and 2 gain stages. The differential input pair input is implemented with PMOS transistor to reduce the 1/f noise. This structure is common to the both amplifiers A1 and A2. For our application, the amplifiers don't need to have a high CMR because we don't want to reproduce with precision the ECG signal components. Thus, the design effort is set on lowering the current consumption. Amplifier A2 circuit is modified to add a controllable output offset. The only difference is that the transistor M227 in red in the circuit in the output gain stage is modified so that its bulk voltage can be modified by the self-calibration unit. Increasing or decreasing the bulk voltage will decrease or increase the output offset. The bulk voltage can vary from 0 to 0.9 volt without major modification of the common mode gain. The main simulated figures of the amplifiers are a 60 dB differential gain, a 49 cm error, and a 7.5 nanowatt power consumption for each amplifier. In this work, we have implemented a conventional threshold comparator to generate the clock wake-up signal based on the comparison between amplified differential signal and the reference common mode signal output from A2. The power consumption of this block is 4.2 nanowatts. Self-calibration unit acts as a feedback loop to adjust the A2 output offset voltage. The calibration of the system is done by comparing the mean of the output voltage to two externally set patient-specific reference voltages. If Vc is over the high reference voltage, it means that the additional offset component VO is too low and needs to be incremented. Reciprocally, if Vc is below the low reference voltage, VO needs to be decremented. Once the calibration is done, there is no need for further change online, and the self-calibration unit is put in sleep mode, decreasing the power consumption. The overall circuit has been implemented in CMOS 28 nanometer FD-SOI technology and simulated at transistor level with Pacemaker. The ECG signal used for simulation and validation has been generated by the ECG scene application from FusionNet and includes the ECG components plus motion artifacts, baseline drift, and 50 Hz noise. The top graph shows the input ECG signal wave with the main components used for simulation. Vertical lines are the marks for verified heartbeats and represent the exact position of the peaks. This middle graph shows the output of both the amplifiers A1 in blue and A2 in orange. The high differential gain of A1 allows to extract the expected heartbeat peak. We can also see on this graph that the reference common mode voltage is reactive and tolerant to environmental perturbations and variation such as baseline drift or motion artifacts. The last graph shows the output wake-up signal obtained with the heartbeat detector. We can easily see that the wake-up signals pulse and the beats are concordant on the graph. For long-term wearable application, the main constraint is put on power consumption. That's why we propose to compare our circuit with the state-of-the-art ones through this one factor. The power consumption of the other circuits studied for the state-of-the-art is degraded either by the need to have a high CMRR or by the fact that threshold calibration is always on. The results obtained for a circuit at 60 bits per minute are 15 nanowatt consumption for the different serial amplifiers, 4.2 nanowatts for the comparator, and 4.2 nanowatts for self-calibration unit. Since the self-calibration unit is in sleep mode while online, it results to a system power consumption of 19 nanowatts only. The figures are obtained by simulation in this work, where the power consumption of the state-of-the-art circuits are obtained by measurement. To resume this presentation, we propose the two electrode heartbeat detectors using common mode voltage as a decision threshold. The system doesn't need a high CMRR for amplifier design, and its patient-specific self-calibration of the circuit is done once offline. The system has been validated by transistor-level simulation using real ECG signal from the FusionNet database. The circuit showed the power consumption performances below the state-of-the-art and is suitable for embedded systems. In addition, the two electrode sensing reduces the number of sensors on the patient body and is more comfortable. Thank you for your time and attention. We want to acknowledge that this work was supported by the European project JEDI, and if you have any questions, feel free to ask or send email to the following addresses. We will be pleased to answer you.
Hello everyone, my name is Lionel Levine, and on behalf of my research colleagues, thank you so much for your interest in our work, and thank you to the conference organizers for giving us the opportunity to present our research. Today I'll be presenting on anxiety detection, leveraging mobile passive sensing. A quick background, as noted, our focus here is on anxiety, which is the largest and most common class of psychiatric disorders in the US, with it being estimated that nearly 1 in 3 individuals in the US meet a full diagnostic criteria for anxiety. Here we see sort of a breakdown on the total US population, with, for instance, anywhere from 7 to 9% of the US population suffering from diagnosable phobia, 7% from anxiety disorder, and 2 to 3% from panic disorders, agoraphobia, generalized anxiety disorder, or separation anxiety disorder. It should be noted that people suffering from anxiety tend to contend with substantial distress and impairment throughout their lives. They are at heightened risk for a host of negative long-term outcomes, including anything from depression, substance abuse, and poor physical health. In general, the optimal methodology for the treatment of mental health tends to focus on early identification, diagnosis, and proactive treatment. However, it should be noted that most traditional methods, including clinical interviews, self-reports, are limited in their capacity to do just that.
And that's true for individuals who are actively receiving treatment. Anxiety specifically is a vastly undertreated condition, with it being estimated that at most only 30% of individuals receive treatment of any kind. And with young adults that who report in some instances up to 60% of college-age youth reporting anxiety, they are demonstrably underrepresented in terms of treatment. As a result, there remains a pressing need for tools to improve early identification of anxiety symptoms, provide users with the capacity to monitor activities, raise awareness of factors impacting their well-being, and provide a mechanism for intervention and treatment should the need arise. If you are in this conference, the capacity and potential for smart devices to impact on an individual's health is probably well established for you, so I will not dwell on this point except to note that while there has been significant success in monitoring physical and physiological health, mental health has seen comparatively less success. Where we have seen the most success is using wearable sensors such as those embedded in smartwatches to monitor things like heart rate variability and galvanic skin response to detect acute stress levels. In contrast, more abstracted measures of mental health, leveraging an individual's behavioral patterns, although such patterns are obviously intimately linked to an individual's mental health, are more difficult, and we have seen comparatively less success in that domain. An obvious challenge to this is that in addition to the challenges around successfully and accurately monitoring behaviors, there are significant heterogeneity in behavioral patterns, both within users and across users, most of which are not directly attributable to a person's mental health, that confound easy analysis of and classification of individuals' mental health. Nevertheless, we have seen a number of very promising recent work in this domain where individual studies have leveraged anything from motion sensors, ambient light, an individual's microphone, camera, GPS, proximity, and touch screen in an attempt, by and large, to classify users' self-reported measures of depression. And we note in the paper that while we have seen, while these are very promising, none of these have advanced to a mature, fully capable framework. Such research has focused almost exclusively on depression, which, while often spoken of in conjunction with anxiety, does manifest in distinct ways. Now, we have sort of already talked about sort of the notions of the opportunities and the challenges, but obviously having a phone which is ubiquitous and typically on the person for most of their waking hours allows for continuous collection of quantitative data and can potentially provide a more reliable indicator of an individual's mental health at any given point. Its nature also as a sort of remote point of care modality allows for sort of just-in-time interventions as well. However, we've already sort of noted some of the challenges, but smartphone-derived behavioral data does present a number of challenges, including trying to infer behaviors which can be done at best indirectly and often inaccurately. To that end, we introduce our research. So our colleagues and I have developed a platform called eWellness. It's a system for the remote monitoring of mental health symptoms. The wellness framework is designed to capture a broad spectrum of remote monitoring, survey data acquisition, secure data transmission and management, data analytics, and ultimately data visualization as well. The primary component of eWellness is a mobile application that facilitates user collection of data collection of an array of sensors and user logs from an individual's cell phone. This data is collected passively, which is a critical enabling factor because it does not require the active participation of the user in data collection activities.
This data is pre-processed, transmitted securely and encrypted in formats to a remote server where it is stored and indexed. We also have the capacity to conduct active surveying via ecological momentary assessments, where we can actively query an individual for their mental health at any given point. Data collection. So looking at this architecture from the ground up, so our hypothesis is that anxiety detection or classification is possible if we can sort of actively build a model of an individual's behaviors and their sociability. And to do that, we leverage an array of communication logs, embedded sensors, and user logs. To give a specific sort of rundown on the types of data that's collected, so for communication, for instance, we monitor and log all incoming and outgoing calls and text messages, as well as the duration of calls and the number of unique individuals contacted. And we'll speak more to this, but again, we should note that we are simply logging the raw numbers. There is no associated content associated with that. Similarly, for location, we attempt to query the total distance traveled without tracking any of the specific locations in individual visits. Ambient sound, rather than recording specific audio of an individual, we simply monitor the decibel level of the individual's environment and record both the decibel level and the frequency of the associated sounds. You can see here activities and movements are tracked, light usage as well as phone usage are also monitored in a similar manner. Privacy. So this is kind of an interesting balance that in designing the research methodology for this, we've kind of attempted to sort of protect an individual's privacy given how potentially invasive this data collection can be. And as a result, we've carefully scoped the data to avoid the collection of anything that could be considered PII or personally identifiable information. So, I already kind of mentioned the example of sociability, where we log the total number of calls, the total number of unique contacts, and the duration of those calls, but none of the identities or the underlying content of those calls is monitored. And this has the consequence of introducing sort of an interesting degree of obscurity in that while we can see that a call is made, we have no context as to whether or not that was a positive or negative call. So the example I always give when I do it is if an individual spends 45 minutes on the phone, we don't know if they were catching up with their best friend or on hold with customer service trying to get their internet back online, which would obviously have dramatically different impacts on their mental health. Specific to our research methodology, we conducted a pilot within the university community where we recruited a dozen individuals. Individuals were asked to download and run the eWellness application for a month, during which time the previously mentioned data was collected passively and continuously. In addition, users were asked daily to fill out an EMA, specifically the Kessler Psychological Distress Scale, or the K10, to provide us with a label of their mental health and their anxiety on a given day. The results of it. So of the 12 that were recruited, 10 participants successfully completed the study. As our analysis focused solely on fully supervised learning, only days in which we received a K10 label were included. As a result, in total, we collected about 146 daily samples. Now, the K10 breaks down into four class classifier, as you can see on the top right corner, with low distress, moderate, high, and very high distress as being the four classifiers. We then applied normalization to the daily samples that we collected, and then looking at the statistics, we trimmed the total number of features to the top 25 that correlated most closely with the raw K10 score. And in the paper, we go through precisely what these features are, but you can kind of see them on the table here, the features we ended up running our models with. Now, for the classification exercise, to do that 4-class classifier, we did a 5-fold cross-validation and we tested it on 4 different models. The class weight was automatically implied inversely, such that low stress, for instance, had a much lower weight than moderate or higher stress, given the relative frequency of them. Using this under this sort of limited learning model, we achieved an accuracy of 76% using the extra trees model. We also attempted to apply an undersampling technique in which we randomly downsampled the low, and we eliminated the ultra high stress category to make it a three class classifier. And you can see the result of the confusion matrix here for that result as well. In the discussion, we do mention sort of a number of kind of interesting takeaways, but one of the things that I wanted to call your attention to is labeling accuracy. And part of the reason why we didn't attempt to sort of build a more robust classifier model, firstly, just by nature of the amount of data collected, we weren't fully confident in building a fully robust model anyway. But I think in addition to that, one of the things that we realized in running the study was that there was significant concern about how accurate the labels were that we received. And if you recall, so the labels in this case are solely from user self-reported labeling of mental health. And what we came to realize was that there was significant inaccuracy in how users reported their own mental health. And we sort of mention here a few of the sort of underlying causes. But one of them is that we were able to monitor whether or not people actively submitted their questionnaires, but we had no way of doing any sort of cross-validating to confirm that what they were submitting was accurate. And it is highly likely that users, in order to sort of complete the study, would fill it out quickly, but not necessarily accurately. There's also significant concern around the stigmas associated with mental health and reporting that out. And then finally, there's the problem of standardizing both within and across users, where even users who are well-intentioned and want to report accurately won't necessarily be able to do so perfectly accurately, and how an individual user recalls certain stressors will tend to vary significantly. And as a result, we realized that the labels we were working with were of highly questionable veracity. And that is, I think, a key concern, not just within our own study, but in general when it comes to attempting to do classification with something as nebulous and amorphic as mental health, is sort of improving the methodology to ensure that we're working with fully accurate labeling. The other thing that we'll note, sort of in a more positive light, is subject heterogeneity. So, we did note early on that users' behaviors will vary significantly, and we talk about that a little bit in the paper. And as a result, we sort of assumed that ultimately this model, we would see more success in classifying within individuals over time rather than across users, just given how diverse and varied and different people's behavior patterns are. In this case, given the relatively low number of subjects and data points, we weren't able to run that kind of test, so instead we just simply had to bundle all the samples. The fact that we were therefore able to achieve the kind of classification success we did, given that underlying heterogeneity, is remarkable and does indicate that cross-subject learning is possible and certainly worthy of further work. We do speculate that part of the reason for why this could be achieved is because we did normalize the data. And one of the consequences of data normalization is that that sort of diminishes the importance of the absolute raw numbers of data points, whereas instead focusing on variances and shifts in user patterns, which are far more likely to be reflective of mental health than the raw scores associated with them. Finally, we'll note the usability. Obviously, whenever you're conducting data collection exercises, privacy and security concerns are foremost. So we did want to sort of query our users and understand whether or not they found that the level of data collection was acceptable or overly intrusive. And as we note, no individuals found it overly intrusive, no individuals declined to participate, and virtually all individuals felt comfortable with the level of data collection that we achieved for eWellness. Thank you very much for your time.
Welcome everyone to the closing ceremony of BODYNETS 2020 conference. We would like to make a few important announcements, but before going into the announcements, just a quick recap about the history of BODYNETS. Started from 2007 and this year 2020, where conference was supposed to held in Tallinn in Estonia Technical University. However, we have, due to pandemic, launched the conference in a virtual mode. And I really hope that you had a good day on the BODYNETS conference and enjoyed the technical sessions as well as the keynotes that were presented earlier this morning. So the announcements regarding the Best Paper Award. So it's time for that. And this year, the Best Paper Award goes to on the ultra-wideband in-body propagation measurements using pork meat. The authors are Mariella Ceres Toniemi, Carlos Pomolaza, Chemai Kisi, and Yari Linati. Congratulations to all the authors of this very good work, and which has been selected based on the rigorous reviews and by the unanimous decision from the organizing committee. So a lot of congratulations to the authors. Next announcement is regarding the next year BODYNETS 2021. And we would like to invite you to join us for the next edition of BODYNETS 2020 in Glasgow, Scotland. So basically the conference will be led by Communication Systems, Sensing and Imaging Research Group by Professor Muhammad Ali Imran at the University of Glasgow. So we really look forward to see you hopefully next year in BODYNETS 2021. So from this, I would like to say thanks to everyone for joining for BODYNETS conference and hope to see you soon next time. Thank you very much and goodbye.